No, hai ragione. No, X dentro il caletto. Grazie mille, scusa che non ho fatto prima. Abbiamo la stessa prima. Sai? Not lead di pendrive. Yes, fine. Yeah. Okay, sì. Ok. Abbiamo 1, 2, 3, 4, 5. Poi ci mancano le altre. Esatto. Sì. Questa ci sono. Sì, sì. Solo per me avete fatto stamattina una presentazione di condividete, lo fate voi o se no lo faccio io così. Condividere la presentazione.
La prima?
Sì. Uso... Ah.
La prima è questa.
Sì, ok, le mani. Ok. Condividere però. Perché
devi condividere quello schermo di giusto.
Sì. Mi sentite? Andrea, mi senti?
Sì, no.
Sì. Vediamo se ci si va. Così stai condividendo questo. Riesci a vedere anche la parte delle note?
No, vedo solo la presentazione.
Ok, perfetto. Grazie.
Allora, okay. So I think we can start. Welcome to everyone. Now we will start the first of 2 sessions about the special workshop, which is called ANAMS. It's advanced numerical approach for assessment and design of non-tension measuring structures. This is organized by Natalia Pignaro, Stefano Galassi, Andrea Montanino. Stefano, I'm sorry, they are not present to be with us. And so this is split up. Andrea, can you?
Yes.
Turn off the microphone.
And now we start with the first one. We have 5.
We have 5 and then 4.
And then the next session we will have 4 contributions. Some of them will be online delivered. So I think
we can start.
Yeah.
So the floor is yours.
I think I'm the first one. So the presentation, the title of the presentation, is DEM investigation of sliding mechanisms in a 3D printed flat arch. Maybe the title can be seen as ambitious, but it is technically the summary of a master thesis done by one of the authors, which is Michele Lanza, which was supervised by me and Francesco Vigariello and Giuseppe Maddaloni. So The main motivation of this work started from a kind of a real problem that we had in an experimental test. Was 1 year and a half ago. It was in Murcia, and it was the analysis of this stereoatomic flat vault, which was designed by Professor Enrique Rabasa of the Polytechnic de Madrid. And this put us in front of a series of questions that we needed to answer, because he asked us for the stability assessment of this flat vault. This is all these images at the beginning are a bit of confidential, because these are part of the paper that we hopefully we can see online soon. And this is the mainly the shapes of these stones. As you see, the shape of these stones is a bit complex. It's made up of this non-convex shape. We will see this soon in details. So, what are the motivations behind the reusing or the of flat vault, stereoatomic flat vault in contemporary civil and architectural construction processes? So, first of all, we know very well the construction industry is responsible for most part of the carbon emission. In particular, the part that is the use of steel in our everyday construction is responsible of 60% of carbon emission of our of this CAI sector. And we strongly believe that one of possible strategies to overcome or to at least reduce the carbon emission of this construction is to work on the slab of the slabs or reinforced concrete slabs in order to achieve best performance while still using compressive stones and reducing the use of reinforced slabs. And one idea is to reuse in a modern, the same logic that was used by old master metals in a new kind of modern shape. And the idea is to, at the moment, is to place, to put attention on this reinforced concrete, on these vast stereoatomic vaults in order to achieve some advantages like splitting up the two parts that are working, one in compression, the other one in tensions, completely divided. So in order to allow for a more performant, a more, I would say, advantageous reusing the strategies. And at the same time, allowing for the easy disassembling process in order to disassemble and to rebuild maybe different or maybe the same structures in another place with the same material, so reusing the same material. So this is the geometry first challenge, but there are many challenges connected to this shape. The first challenge is the geometry of the flat vault, which is very complex. And as you see, it's composed of non-convex blocks. And when you start looking from a numerical perspective to the mechanical behavior of these non-convex blocks, you know that there are many problems arising. And a strategy can be the composition and then rejoining of these two, in the composition into convex shapes and rejoining in non-convex shapes. But there are also this, like in this case, the non-convexity due because of which comes on horizontal plates. So at the first sight, we tried to understand at least the main behavior of the works. This was the geometry that we were able to reconstruct in 3D. And this was done in Rhino. We processed all the things in Rhino, which is a CAD software. And then we were able to build this 3D model. And the first thing that we were wondering about was the minimum thrust behavior of this flat vault, because we know very well that this, and we'll see this in the presentation, that these kind of systems, they work mainly in a minimum thrust condition. And to achieve this, we wanted to see what was the behavior while we were moving outwardly the supports away from the structure, just a little bit. But the only answer that we were able to get from 3D was this. So a color map of the flat vault without any kind of engineering meaning behind this. And so we were wondering on what we can do more and better to understand the behavior. So the first line that we wanted to explore is to how reinterpret the 3D result in a different way in order to get the engineering answers. And so this was the motivation behind this process. No, it's okay. It's okay.
Because I was trying to
Open the air conditioner.
Fatal error.
Okay. Okay. It's okay.
because it's too hot.
But I don't know how to.
To reset.
Yeah, indeed, it's too hot. I'm Sweden.
Yeah, I agree. It is too hot. Everything seems.
Sorry.
No, but it's okay. It's okay. It's just a.
It just doesn't work anything.
No. There's no power. Electric power. We will.
It was very interesting. I wanted to know how it's ends. No, assolutamente. C'era era proprio volevo vedere come andava a finire, mi interessava molto.
Ecco.
Ah, ok.
Vai.
No, this is
Ma quanto d'ora prima che ti...
I will never forget this.
Andrea, sei ancora online?
Andrea,
Sì, ci sono.
Ok.
Cosa sta succedendo?
il professor Milani ha staccato la corrente dell'aula.
Ah, ok.
Io non lo so fare questo.
Però funziona ancora tutto.
Diciamo che se fosse in inglese sarebbe stato un po' più semplice da capire, ma... Someone of you know Portuguese? No, perfect.
What are you trying? Can you translate it to Lance?
Yeah, maybe.
Do you want to enter one of these?
Entrada, probabilmente. Yeah. Yes.
You have already?
Yes. Okay, I think it's all right.
It's
It's working.
Okay, looks like this is perfect.
No, it's only now. I think it's on the and
Oh, this is just in the after.
yes.
Yes.
This is listed, right? If you have, hold on.
Ok.
Okay, yes, you see.
Si vede lo schermo, Andrea?
Sì,
Senza le note.
ma non si è mai staccato, non è mai cambiato niente qua.
Ok, perfetto.
Perfetto.
Okay. So this is more or less how we will go quickly to these sections. This is the structure of the work that Michele and Ansa, our master student, did to start looking at this problem. And here I'm in an environment where, you know better than me this mesory topologies. So what is a flat arch? We know that even in ancient time, where curved arches were strongly used, people were used to build, to span distances using flat arch technologies. Like in this case, like this example, which is one of the most famous and most ancient flat arch in the world, which is in Baalbek in Lebanon. And these are two pictures which are 150 from shoulder. And the arch is in the same position, trending the same low conditions. Andrea, can you turn the microphone off? Thanks. Another example is this one in Greece, and we know very well that ideally we can, even from looking at an example, a marble beam, we know that tensile stresses, as in the middle picture, can arise, and then it cracks, and then we can have a flat arch that can stand to this 3-inch shape. many other examples in our architecture, from Pompeii to Rome to Viterbo, ancient use of flat arch. And we know very well that in the last 200 centuries, they were used, particularly in French, in Germany, and in England also, to create flat slabs. So we were wondering on how to study this better, or even better, how to use 3D for this study in order to catch the behavior of the flat arch and translate this all the numerical codes to the flat slab. Usually, proportions in a flat arch goes when you look at the ratio among thickness and span. They goes from 1/2 to 1/8. And the joints are typically flat, but in some cases, like in this, they are not. And there were many studies, just one here, one made by Coulomb, to understand what is the best joints layout to stand without any kind of friction, or with zero friction, on an arch and on a flat arch. And you can see that you can derive a flat arch from the joints layout of an arch, like in this figure, simply this way. This is a graphical way to ideally the flat arch that you can see on the tops should stand without any friction. When we look at these problems, usually we are very well. We apply the Hamann theory, which stands on these three main assumptions, and we know very well that we cannot we need to remove and to test the no-sliding assumptions, because in this case, sliding is very, very important. And in order to apply particularly the lower bound theorem from or better, the safe theory. So these are two typical, and this is an image from Barlow. These are the two typical conditions where an arch can stand in a minimum or a maximum just condition, depending on the stress line, and this depends also on the hinge positions, like in this case. But we know very well that a flat arch, like in this case, it usually lives in a minimum just condition. So when we need to look at the stability of a flat arch, it's much more important, rather than looking at to a maximum just condition, which can be infinite, to look at the minimum just condition, like the one you see on the right, and then connect also the minimum just condition with the overloading scenarios, like in this case. And so the first thing that we say that we need to understand the behavior of the flat arch, even experimentally, by applying outward displacement on the numerical code and checking this, validate this on experimental basis. We use 3D. Everyone of us knows very well what is 3D about, what are the main hypotheses of 3D, what are the capabilities that we can look at the structure as composed of distinct elements, and we can assign any kind of property to these rigid blocks, and we can even kind of remove the rigidity assumption. We can model the blocks as deformable, which is very important for the slab. We can assign joints properties. We can select this kind of interface condition, depending on our way of looking at the problem and on the necessary condition, let's say on the assumption that we want to use for the joints. Usually, and this is very important for the joints, they are modeled with a common plane theory, which means that basically you can model the contact through normal and unilateral normal compressive springs and tangential springs, meaning that somehow numerical overlapping among two blocks over the common plane can happen. But usually this is negligible because we are talking about a numerical, so something that is 10 at -6, -8 meters. We looked at this problem. The design of this arch was done by using the Coulomb rules. So all the joints going through the same point. This is the weight of this source and the buttresses, bit of the graphic statics, and this was the design and mainly what they usually you apply when you use graphic statics in this case. As you can see, this is the minimum friction angles that are needed to make this flat arch stand. And if you want something like a zero friction behavior, you need a truss line like the green one, which goes exactly orthogonally through all the joints, meaning that the buttresses should be designed with these dimensions in order to make the truss line going down in the within the on the footprints. So the parametric investigation, as I said, was done in Rhino. We made analysis 3DEC, but we needed to post-process all the 3DEC analysis because from the 3DEC main results, we were not able to catch any meaningful conclusion. This was, in this video, you can see what we did, all the parametric scripts that we did with Mechanic and Rhino. After that, we were able to create all kind of geometries, say, this geometries in 3DEC. This is a typical 3DEC analysis, you know this very well. And then there are a few scripts to get all the 3DEC properties out of 3DEC, and we were able to post-processing all this stuff in Python to reconstruct geometries, to reconstruct interface over blocks overlapping, a lot of numerical stuff. And like in this case, you can see this is a simple reconstruction of the 3DEC analysis made in Rhino. We analyzed these three models with these three ratio of thickness and span. The first one, these are 3DEC analysis. You see, typical 3DEC window. And this is the post-processes that we did in Rhino. So you see the trust line, how it evolves when the external data goes away, and so on. But not only this, we were able to understand the ratio among normal and tangential forces over joints, and to understand when it starts sliding, when it starts creating an inch, and so on. Like in this case, first, when you see all the trusses that are going up, like asymptotically, vertically, this is exactly because you have the three inches are going to be aligned. Or in this case, you see, this is the result with a 5 degree of friction capacity. Mainly what you saw at the beginning was that you see sliding all over the interfaces, and then it starts hinging when it's close to the collapse mechanism. This is the behavior, but I don't have the image, with the 35 friction degrees. You know, the sliding is avoided from the beginning because the truss line cuts the joints with an angle that is less than 35 degrees. And then he has a typical 3-inch mechanism with the collapse, which is also demonstrated by these diagrams, where you have the trace of the normal and the shears over the weight as a function of the displacement of the right buttress. And this is, for this analysis, the comparison among the ratio T over N and the friction capacity, which is around 0.7. As you can see, it's always below the friction capacity. This is why it's always hinging and never sliding. So these are the two comparisons among these two stuff. What is nice in this example is to look at the maximum displacement, which is more or less the same for this. But this is due to the one fact that we were simply moving rigidly the other buttress away. So without allowing the buttress to rotate around the base corner or something like this. And this is something that you cannot mostly for all over the analysis that we're able to do. And to understand this better, we have performed physical tests with the 3D printing a block, then putting sand inside, then making this test. This is the test with 5 degrees, with the friction angle that is more or less 13 degrees, which is the friction between PLA and PLA. And to catch this behavior, we create after the calibration of the model that we did before, we create exactly the model that you can see here in the test, with the friction among the blocks, which is measured over the test and so on. And we were able to catch the behavior with the same displacement capacity. This is the last step for the collapse, and then you will see the green arrows here, which are showing that the other buttress is going to rotate. And this is the same analysis made with the higher friction, placing sands over the interfaces. So you see always hinging. And the same model up in 3DEC, very well calibrated, you see the collapse with the rotation of the buttresses. And this point, in these two cases, we were able to catch exactly the same collapse mechanism that was calibrated before. We did also some analysis on the position of the thyroid, which was very important for the understanding the stuff in the Murcia, and also to connect this kind of minimum task condition with the thyroid tensile forces. And you see, this is the first analysis did, and this is the collapse 4 inches with this layout scenario where the thyroid is placed at the bottom part of the flat arch. And this is another placement of the thyroid increasing. In this case, what we noticed was that it was able to stand this load without any collapse mechanism. And these are the two diagrams which are connecting applied load with the thyroid elongation. In orange, the one that you can see on the first position on the bottom, in the blue in the middle, and the red, the curve that is representing the thyroid force that was measured on the laboratory test. So in the end, this was kind of all the physical and numerical tests that we started with Michele to understand, in order to understand the behavior of the blackboard in Mursa. Then we developed in the last years a few more things, also with Lina, and we present this today. Our aim was to start understand, well, to start calibrating the 3D model, to use the 3D model in order to get the behavior of this flat arch, to go first from the flat arch to something that was three-dimensional, that is the flat stub in use. I'm okay, I'm done. Next.
Thank you, Nino, for your interesting presentation. Are there any questions from the audience?
So, yeah, it is a very interesting topic. I studied this, and for example, the fact that Coulomb demonstrates that a flat arch can maintain equilibrium even though friction is near. It's a very interesting topic. I have noticed that when you suppose the movements, you suppose that the two fires move apart.
Yeah.
Yeah, but instead, if you assume that they are fixed, so friction, I think, plays an important role in bearing capacity. But have you investigated also this type of solution?
Well, honestly, not probably while completely fixing the two batteries. What we did, just to catch more or less to start understanding the behavior of the flatboard, was let's try to have a kind of meaningful comparison on a 2D model of the 3D behavior of the flatboard, like in this case. So without fully restrain the two batteries. So I would assume that this would be very interesting, that if you, in this case, if you are able to, somehow, in an experimental test, to fix these two batteries, but then you have to carefully also take into account the deformability and all the other stuff, as you know, then it's going to be very interesting to understand the role of the friction capacity also, because you may have, this extremely well, some blocks moving up, some moving down, and you can have a mechanism that can be very difficult to control.
Yeah, because tires could also simply rotate and not slide, for example, or be fixed. Yeah, but I think it's a very, very interesting topic. Thank you for the word.
Other questions? I think we can skip to the next presenter, which is Sara Noracci, a PhD student from Politecnico di Milano. She will present a work titled Defining Modeling Priorities for the Seismic Assessment of Mineral Structures, Geometric Sensitivity Analysis. And so, please, Sara, the floor is yours.
Good afternoon. I'm an architect and PhD student from Politecnico di Milano, and today I am presenting our research in collaboration with Hani Hassan from National Oceanography and Geophysics Institute in Salonico, Italy, Mariam Salam from National Research Institute of Astronomy and Geophysics in Egypt, Professor Gabriele Milani, and Professor Marco Valente from Politecnico di Milano, Department of Architecture, Built Environment, and Construction Engineering. And I would like to begin this presentation with a reflection of my home country, Turkey. It's a region historically defined by destructive earthquakes, as recently seen 3 years ago in the Turkey-Syria earthquakes. And here we understood that seismic events do far more than claiming human lives. They also disrupt our physical space and connection to our collective memory through cultural heritage monuments. And one of the typologies of monuments in Turkey are the minarets, which stand as outstanding witnesses of the seismic actions. Minarets are highly vulnerable to earthquakes due to their extreme slenderness and also the weak mechanical strength of masonry materials. Historical records often show recurring patterns of failure and collapses. Yet, seismic design and preservation guidelines in countries that have a significant inventory of this typology do not cover these features in their building code. The academic literature, on the other hand, is expanding. However, most research on the seismic vulnerability of masonry minarets are singular case studies that specifically study a structure adopting sophisticated numerical approaches. While they are providing valuable and very detailed results, these methods are computationally and time-wise expensive, and they are highly sensitive to modeling assumptions, including the geometry and physicality of the structure they represent. They can, in this case, the practitioners can often choose to simplify these models by removing certain segments, also depending on the data that is available to them, which can affect the trajectory of the assessment procedure. Another approach that can be used as a robust alternative to the advanced approaches challenges is kinematic limit analysis. It is a simplified tool that can estimate the probable collapse mechanisms based on some predefined and demonstrated in real life failure modes. It requires significantly less input data and computational time and cost. It can be also managed in hand calculations and is an accessible tool. So its application to minarets currently is very limited, but we here intend to develop it as a standardized approach for minarets in the preliminary seismic assessment stage for a large inventory of structures across a large territory. And in this particular study, we are analyzing through two main approaches, the analytical and numerical validation of the effect of the simplified geometric features, also structural features, in the results of our modeling assumption, in the results of our processes. So we are looking at the staircase, transition segment, and balcony and wall thickness changes along a minaret, and what happens when we ignore or simplify these features in the finite element analysis and kinematic limit analysis. To contextualize our study, let me first define the architectural layout of a minaret. They are towers integrated within mosques with a primary function of reciting the call to prayer to believers from an elevated point. And to support these structures against gravity, winds, and seismic actions, especially in an active seismic context like here we focus on, builders developed historically different geometric configurations. For example, in Iran, the minarets usually have a monolithic body with a tapering geometry with a decrease in the cross-section. In some styles in Egypt and Ottoman styles, including Turkey and Balkan countries, they exhibit distinctly segmented profiles also because of the function of the minarets. And as illustrated here, these minarets, this one in Turkey and Egypt, they typically initiate with a rigid base connecting to a tall and slender thin body through a transition segment, and along the body there are several balconies, and they actually divide the body into different cross sections. And each balcony is reached by an internal spiral staircase. And owing to this segmentation and exceptional height of the structures, there are certain seismic, also structural vulnerabilities. So turning back to our current research, we wanted to evaluate the simplified features in two distinct settings. From Istanbul, we took the Hagia Sophia Mosque minaret as a stone masonry minaret from 16th century and a 17th century stone minaret from Egypt, Cairo. These structures represent different material properties and height classes. One is about 7.6 meters and the other one is 27.5 meters. And as you can see, for example, in Hagia Sophia minaret, in the boot part, there is a change in the wall cross section. And in Marzuki minaret, for example, the entry to the minaret is above the ground level. There is a very high bulky section. And as I said, one is significantly actually shorter than the other. And previously, some parametric studies have already examined the effects of openings like the little doors and windows, the spires, stairs, and inclination of the minarets. And here we currently focus on the wall thickness changes and tapering, presence of the transition segment between the boot and the slender body, stairs, and balconies. And to systematically isolate and quantify their impact, we developed 4 modeling scenarios for each. The base model disregards all these features that we examined, and the model with in this one is the most accurate one. Then we exclude the stairs and balcony in the 2 and 3. And we created finite element models on straws using solid brick elements. So we first subjected all 8 models to model analysis, and looking at the model mass participation, we observed an effect of the staircases. Here, as you can see on model M1 and 3, when we have the staircase, the mass participation ratio along 2 main directions are quite polarized. So this indicated that in the lack of stairs, in the base model and the stairs lacking model, a diagonal axis of vibration must have been formed to bring those ratios alignment. And in Hagia Sophia, this was not apparent. We can attribute it to its greater height and more uniform profile that override the aspect of the stairs. And in both minarets, the dynamic response was dominated by the first 2 modes. For the taller Hagia Sophia minaret, the individual features, like only the balcony or only the staircase, had a minor impact, but all the cumulative impact of them exhibited an increase in the fundamental periods. In the Marzuki minaret, removing the balcony had decreased the fundamental periods, and this was not so significantly observed in Hagia Sophia minarets. To look at how the modeling approaches diverge from the original models, we created these charts. The negative values indicate an overestimation, and positive values indicate a conservative estimation. In Hagia Sophia, omitting all secondary features resulted in an 18% increase of the fundamental period, and for the shorter Marzuki minaret, removing the balcony led to a 10% decrease in the period. This is larger than in Hagia Sophia, which indicates the importance of the height class of the structure. Secondly, the mass effect of the balcony must have been more important than the stiffness effect. In the second stage, we implemented kinematic limit analysis with masonry 0 tensile strength. And taking the architectural segments as the macro blocks, we considered core collapse mechanisms the collapse from the base, from the upper segment of the transition segment, from the upper body and balcony. And we considered modal load distribution, calculating the seismic collapse multiplier for each model. In the end, mechanism 1, the collapse from the base, was considered in all scenarios. The examined features did not change the active failure mechanism, but they changed the collapse multiplier value, especially for the higher levels. In Hagia Sophia, due to wall cross-section changes, the capacity for mechanism 2, for example, was overestimated by 5%. In Marzuki Minaret, the balcony caused a greater decrease of 18%. Because Hagia Sophia has a much larger upper body mass, the effect of the balcony alone was less prominent on its response. And finally, we performed nonlinear static pushover analysis with the 2 edge cases of Marzuki Minaret, the baseline and the accurate model, the original model. And the resulting capacity curves revealed that here we stopped the analysis at when the convergence was lost, and we adopted more clone failure criterion. So in this horizontal load, the baseline model overestimated the capacity by 12%. Despite this, the principal stress and strain contours did not change, but they confirmed the plastic hinge location at the base of the wood, as was found in kinematic limit analysis. And collectively, these findings indicate the importance of modeling the secondary features. Accurately modeling the transition segments and balconies, especially for structures that are shorter, is important since their local mass contribution and concentration can dominate the response in terms of the periods and the local collapse modes. And secondly, the significant wall changes, like in Hagia Sophia here, should be considered. And staircases, they have an effect on the model shapes and the mass participation directions, but they have less effect on the global capacity. And we can also finally say that kinematic limit analysis was an efficient tool here by the agreement with the finite element calculations in predicting the collapse mechanism. In future studies, we intend to expand the benchmark diversity and also apply the pushover analysis on the other scenarios, and also investigate how to include the no-tension material assumption in the finite element phase to compare them with the kinematic limit analysis better. Thank you very much.
So thank you, Sara, for your interesting presentation. Any questions from the audience? Curiosity?
I have just a curiosity. Thanks for super interesting work. Based on your expertise about this, what would you think the relevance or the weight of the elasticity in these results? The elasticity in compression of the material. So, what is your opinion also numerically? If you try to.
Currently, I didn't investigate this much, but the brick minarets are usually more fragile in this context. Maybe we can interpret from that point. Thank you.
Thank you for your presentation, very interesting. On the curiosity, sorry if I have, probably you have said this, but when you do the kinematic limit analysis, the hypothesis is that you haven't any tensile strength between the portions of the minaret. Yes. But it could be an idea to consider the effect of the introduction of a limited, small tensile strength, which could be simulate also an interlocking between portions and parallel to separate in the finite element model, in order to have a comparison about the results. Also, on the one side, it is interesting, as you have told, to introduce the notation hypothesis in the nonlinear, in the elastic analysis, finite element analysis, but also to introduce the tensile strength in the kinematic approach.
Yeah,
Could be.
I need to make them also more comparable and more accurate.
Yeah. But there are, according to you, there are connections or not in the reality as a constructive techniques?
Sometimes, in some cases, there are connections also between each span block. But thinking that these each segment actually represents a distinct portion and they are vulnerable, here we were fine with removing that connection.
Okay, thank you.
Thank you. Thank you very much.
Thank you, Chiara.
Perché la presentazione non è stata dispensata, questo è si è portato così
Make a start standing on sheets.
No, I don't.
That's it.
Thank you.
Vediamo se mi chiede perché non hanno visto la versione. Sì, sarà sia scollegato. Ora sì, guardo. Chiedo se
Okay. Yes. Okay.
Okay, thank you. So we are going to the third presentation. A work done by Mohamed Farfuladi, Natalia Pingo, and Gabriele Milani. The title of the work is Parametric Stereotomy Interpolation and the Evolutionary Optimization of Circular Skew Mesory Arches via Upper Bound Limit Analysis, and this will be presented by Natalia Pingo. Thanks, Natalia. The floor is yours.
So, good afternoon to everyone. This work, as Antonino said, was done in collaboration with PhD student Mohamed Farfuladi, me, and Professor Gabriele Milani, and the title is Parametric Stereotomy Interpolation and Evolutionary Optimization of Semicircular Skew Mesory Arches. Here we can see the outline of the presentation. So we start with the context and the motivation behind the research, then we see the research gap and the key idea on which the work is based, then the methodology used, the results and validation, and finally I will draw some conclusions. So let me start with some context, and single span skew arches are an incredibly common structural typology across European infrastructure. They were built extensively during the 19th century on rail bone because the geometry of a skew arch allows a bridge to cross a canal, a road, or another rail line at an oblique angle, which is not necessarily at 90 degrees. Many of these bridges are still in active service today, carrying traffic loads that far exceed what their original designers ever anticipated, I would say. Now, what makes these structures challenging from an engineering perspective is that, unlike a normal square arch where you can reasonably assume two-dimensional behavior, a skew arch behaves in a fully three-dimensional manner. The truss lines are not planar, they generate lateral forces, non-uniform stress distributions, and the collapse mechanisms are a complex 3D phenomena. And this is precisely why accurate modeling of the arrangement it is important, what we usually call stereotomy. Historically, engineers have used three main construction methods for skew arches. The first is the false skew method, where the bed joints are simply parallel to the abutment. This is the easiest way to build, but it becomes structurally vulnerable at higher skew angles because the blocks tend to slide against each other. The second is the helicoidal method, which uses spiral joints to maintain orthogonality with the arch face, within the arch face. The third one, and I would say also mathematically most elegant, is the logarithmic method. Here the joints are kept perpendicular to the arch face at every elevation, which minimizes the risk of sliding failure. Now, here is the critical research gap. In the literature, these three methods have always been treated as completely separate, so basically different categories, and there is no continuous mathematical framework that bridges them. And more importantly, nobody has ever asked, could there be a hyperlogarithmic arrangement that performs even better? That is exactly what this study tried to address. This figure shows the unrolled surface patterns for the false and logarithmic methods. You can clearly see how the false skew pattern has straight horizontal lines, while the logarithmic pattern shows the characteristic curved trajectories. Our interpolation factor alpha, we'll discuss this later, will smoothly connect these two extremes and go beyond. So this is the core idea of our work. We define a single scalar parameter, which is alpha, that serves as a continuous bridge between all construction paradigms. When alpha equals 0, the engine produces a poor false skew geometry with straight bed joints. When alpha equals 1, we recover the classic logarithmic layout. Any value between 0 and 1 gives us hybrid configuration. But the interesting part is what happens when alpha exceeds 1. We enter what we call the hyperlogarithmic domain. No one has systematically explored this space, as far as my knowledge is. The blending equation is simple. The position vector is a linear combination of the false and logarithmic coordinates weighted by alpha. For values beyond 1, we use an angular extrapolation scheme with a small epsilon bound to prevent numerical singularities near the spinning points. As you can see on the right, the color-coded visualization shows how the mesory pattern evolves from alpha equal to 0 through 0.3, 0.6, 0.9, up to 1.2 and 1.6. The progressive increase in curvature is clearly visible, as you can see from the image. This flowchart shows our complete computational pipeline. We start with the input parameters, so arch dimensions, skew angle, and the alpha factor. A custom C# script in Grasshopper together with the Polybrick plugin, which is a plugin developed by me and by the architect Muhammad Korfulagi. It is already published in Rhinoceros, so can be downloaded. And basically, thanks to this plugin, you can obtain whatever curve structure you want with whatever brick arrangement. For example, I don't know, a cross vault with an herringbone pattern distribution. And then you can import the results obtained into whatever software specifically conceived for structural analysis. For example, you can model the joints as only a mathematical plane to use, for example, in limit analysis, or you can model the joints with their actual thickness. For example, if you are working with finite elements or other methods for the analysis. So Polybrick handles the parametric geometry generation for this process. For alpha less than 1, it applies linear blending. For alpha instead greater than 1, it uses the angular amplification scheme. The generated geometry is then exported to MATLAB, where our second-order programming-based limit analysis solver evaluates the collapse multiplier. This solver is embedded within a genetic algorithm that evolves a population of candidate alpha over 30 generations, searching for the configuration that minimizes the collapse load. The entire loop from geometry generation to structural evaluation runs automatically. Here are the specific geometric parameters of our arch model. We use a semicircular profile with a radius of 2.7 meters and a barrel thickness of 0.6 meters. The total bridge width is 5 meters, and the voussoirs are 0.75 meters long, giving us 41 courses to maintain a width to length ratio of about 0.3, consistent with the literature. A vertical line load is applied at x equal to x divided by s equal to 0.3, which is specifically chosen because it triggers asymmetric collapse mechanism. These are the most critical scenarios for semicircular arches. We compare basically three cases: a straight arch as baseline, a skew arch at 25 and 45 degrees. For the structural analysis, we use an upper bound limit analysis approach. The arch is discretized into hexahedral and wedge elements that are assumed to be infinitely resistant, meaning the blocks themselves cannot deform, whereas the interfaces between blocks are rigid plastic. The failure criterion at each interface is a full three-dimensional Morcoulomb model with both a tension cutoff and a compression cut. This is critical for skew arches because, unlike a standard arch where you might get away with Hyman's assumption, here the angular thrust direction relative to the joint planes generates large shear components. You need to explicitly account for finite friction, finite tension, and finite compression. So this formulation is significantly faster than a full nonlinear finite element analysis, obviously, which makes it ideal for coupling with an optimization loop. The limit analysis problem is cast as a second-order cone programming. The objective is to minimize the collapse multiplier lambda, which equals the total internal dissipation minus the work of both forces. At each interface corner, we introduce specific plastic flow variables, which is lambda t for tension opening, and two sets of three components, each for Morcoulomb sliding and compression cap catching. So the intersurface is bounded by Lorentz cones, and this is mathematically interesting because it avoids the polygonal approximations that traditional linear programming would require. The material parameters represent a general class of stone masonry with joints, so friction coefficient 0.75, very low cohesion and tensile strength, so at 0.015 megapascal, and compressive strength of 2.5 megapascal. These low values approximate nearly dry joint conditions while providing numerical regularization. The genetic algorithm uses minimal encoding. Each individual carries a single real value gene, so basically the alpha parameter, ranging from 0 to 2. The fitness function is the total collapse load computed by the second-order cone programming solver, and we start with a population of 50 individuals and evolve them over the 30 generations. And elitist strategy preserves the top 5 solutions. So we have this size of 5 solution preserved, which means crossover at 80% and mutation at 15%, provide the evolution of our process. We also compute the coefficient of variation of each block volumes as a secondary metric for measure regularity and constructability. In total, we evaluated 2,000 unique individuals, so 1,000 for each skewness angle. Before examining the optimization results, let me show the validation. So for the baseline straight arch at alpha equal to 0, our solver gives a collapse load of about 363 kilonewton. When we reduce the cohesion and the tensile strength near to 0 to approximate the joints with a 28-degree friction angle, we get 241 kilonewton, which matches the analytical calculation of 242 kilonewton almost exactly. Furthermore, for GAX, sorry for my pronunciation, for GAX, I suppose it is correct, and co-workers reported a value of 260 kilonewton for the same geometry in their 2018 study, which is very close to our result. The 4-inch collapse mechanism also matches the expected behavior from the literature, so we are confident that our baseline is well defined, and we can evaluate loads for the hyper-logarithmic domain, which can be consistent. So the plot here shown the total collapse load as a function of the shape parameter alpha for both the 25-degree and 45-degree skew arches. All the 2,000 evaluated individuals are illustrated in the chart. So the first striking observation is that there is a nearly linear relationship between alpha and the collapse capacity. As we increase the bed joint curvature, the structural interlocking improves progressively. The 25-degree arch reaches a maximum of about 1,569 kilonewton at alpha almost equal to 2, while the 45-degree arch peaks at about 1,187 kilonewton at alpha equal to 1.58. Beyond alpha equal to 1.6, the 45-degree geometry becomes physically impossible because block dimensions fall below 2 centimeters. The most important finding here is that the optimal configuration is always found in the hyperlogarithmic domain, that is beyond the traditional logarithmic boundary of alpha equal to 1. This table summarizes the optimal configuration. So the straight arch serves as our reference. So we have the a value of 362 kilonewton. Then the 25-degree arch achieved the highest absolute capacity, but with a coefficient of variation of 0.55, meaning significant block size diversity, obviously. The 45-degree arch has a slightly lower capacity, but much better measure regularity. In fact, we found a coefficient of variation equal to 0.37. So, this figure shows how the collapse mechanism evolves for the 45-degree arch as alpha increases from 0 to 1.6. At alpha equal to 0, we see a classical hinge opening mechanism. So the arch pays by forming 4 hinges, very similar to a 2-dimensional arch. As alpha increases toward 0.6 and beyond, the bed joint curvature introduces a progressive zigzag interlocking pattern. The blocks can no longer simply open at hinges. They are geometrically constrained basically by their neighbors. The mechanism transition from a poor hinge opening to a much more constrained mode involving both sliding and crushing at the interfaces. This plot shows the coefficient of variation of block volumes plotted against the collapse capacity for the 45-degree case, so the CV stays relatively low at about 0.36, meaning the blocks are fairly uniform in size. The 25-degree case shows much more diversity, so the coefficient of variation is equal to 0.55. We conducted a focused sub-study on the role of vertical cross joints, which are often overlooked in the literature. We compared two configurations, vertical joints that stay parallel to the arch face, shown in red, and versus joints that follow the same alpha interpolation rule as the bed joints, which are shown in gray. In both cases, the bed joint trajectory is kept identical. The results are quite stating when we switch from parallel vertical joints to interpolated ones, the collapse load drops by approximately 25%, from 487 to 362 kN at alpha equal to 0, and from 817 to 608 kN at alpha equal to 0.5. What is remarkably is that the failure mechanism remains qualitatively identical. The hinges form in the same locations, yet the capacity changes dramatically. The explanation is straightforward. Interpolated joints create smaller blocks with more interfaces. More interfaces mean more potential sites for plastic dissipation, which reduces the energy that the system needs to dissipate through any single failure surface. So, to conclude the work, first, the interpolation factor alpha provides a single mathematical framework that unifies traditionally disconnected construction paradigms. Second, our second-order comprogramming-based limit analysis rigorously handles three-dimensional friction, tension cutoff, and compression cut, going well beyond classical Eiman assumptions. Third, and I would say most importantly, the optimal configurations are consistently found in the hyperlogarithmic domain, delivering up to 4 times the capacity of the false skew baseline. Fourth, while the 25-degree arch achieve the highest loads, 45-degree geometries offer superior mesh regularity and are more practical to build. Fifth, vertical joint orientation has a surprisingly strong 25% impact on capacity, independent of the bend joint trajectory. And finally, this framework provides a quantitative, I would say, computational tool for assessing and potentially improving the structural integrity of thousands of historical skew masonry bridges that serve today all around Europe. And that's it. So thank you so much for your attention, and I'll be happy to reply to your questions if any.
Thank you, Natalia, for this very interesting presentation. Any question for Natalia?
Maybe I can ask. Sure. I am not very familiar with the building of these arch bridges, but is there also the effect, or how do they build it in multiple leaves? Like, are they interconnecting, or is this skew, is this logarithmic scale or order only appearing in the one?
In a one layer?
Yes, one layer.
Okay, so we are asking if there are examples characterized by the presence of multi-leaves, right?
Yes,
okay.
Do they interlock between leaves in that logarithmic order? Or
Yeah. There are skew arches characterized by different, stereotomy and disposition, different layers, and so on. We have many examples all around Europe. For example, in England, we have a lot of examples of masonry skew arches. I would say, in general, in Europe, for sure, we have many.
Okay.
Characterized by different stereotomies, patterns, and so on. And materials, obviously, materials.
Okay. Another question.
First, another curiosity, but the drawing of the joints provides you planar joints here, yeah, in your model, or they are not in the treatment. You have planar joints, like planar interfaces, or not?
Yeah, they are planar.
And so, how, for example, to maintain orthogonality, how can you manage this aspect?
But I mean, maybe I didn't get your point. You mean if the interfaces follows the orientation of blocks, or if they are oriented some way? I didn't get the point. Sorry, Danila.
No, when you draw your configuration of
geometry.
the geometry, okay. I have noticed that they are also interlocked. You consider also staggering between the blocks.
Yes.
But each block has planar faces.
Okay,
or not.
I understand. Okay, I understand. Not necessarily.
Not
necessarily.
This complicates the model as from the kinematical point of view, or it is approximate the mean of a flat surface.
This complicates a bit the program, the limit analysis program, and additionally, we use not only hexahedral element, but also tetrahedral element.
Okay.
This is necessary because when, for example, if you have to model, imagine a cross vault, okay, which is, let's say, more easy than a skew arch, more comprehensible in this example. When you arrive at the section plane, I mean, where two parts connect each other, you have the problem how to merge the block there in this line connecting the two faces. And so we have noticed that for very complex geometries and very complex stereotomies, we needed to insert and to allow the program to consider different typology of elements. Otherwise, the modeling of these characters is very, very, very complex.
Okay.
If we think to use only one typology of elements.
Okay.
This is the logic.
Okay, any other question? No? So thank you, Natalia. So we will go to the next presentation. We started with funicular analysis of a non-symmetric sail boat. Research done by Danila Ita, Matteo Bruggi, Enrico Malavolta, and Alberto Tagliaccio. This research is going to be presented by Danila Ita. Thank you, Danila. So the floor is yours.
This study, which has been conducted together with my colleagues Matteo Bruggi and Alberto Tagliaccio, and with a student which now is an engineer, which studied this topic during his master thesis work. This contribution is inserted in a research project aimed to apply funicular methods to non-trivial geometries. As is well known, modern measure revolves is a complex challenge due to the anisotropic and non-homogeneous nature of this material. There are in the literature realistic models capable of faithfully representing the structural response of masonry. For example, we have homogenization techniques or sophisticated finite element analysis. But given the difficulty to calibrate parameters in the recent literature, there are still simplified methods which assume, for example, Hyman's hypothesis of an infinite compressive strength of the material and no tension between the blocks, and ideally an infinite friction coefficient. The goal of this investigation is to apply this computational funicular method under Hyman's hypothesis to mesoid structures with complex or non-symmetric geometries to accurately describe the flow of compressive forces under surface conditions. Reference is made to the mathematical programming formulation proposed by Matteo Bruggi, and then also developed by Professor Tagliercio, and recently also by me, by introducing other hypotheses. But we will consider this formulation with Hyman's hypothesis. The case study is a sail vault in the Fortezza Vecchia in Livorno. The history of this fortress begins in the 16th century when the family of Medici proposed to modify the existing buildings and took control of Livorno. Antonio da Sangallo developed the Fortezza plans, which is contained in the Canadira bastion. So this is a view from the inside of the sail vault. We can notice the vertical walls, which intersect an almost spherical surface of the intrados and a central octagonal oculus. As part of a collaboration with the University of Pisa, the North Tyrrhenian Seaport Authority has made available the data collected from a terrestrial laser scanner survey. And this is our starting point. A peculiarity of this vault is that it has an almost trapezoidal quadrangular plan. And here we can see the trapezoidal shape of the plan with the contour lines describing the geometric irregularities. And thanks to Professor Andrea Plenoti, we have such point cloud of the sail vault and all the fortress. And here we can see also the point cloud of the vault is structured using the cloud compare software. In order to apply funicular analysis, in particular based on the force density concept, the starting point is to build a network to study. By means of a geometric processing operating in Rhino, the procedure for obtaining a network with fixed projection on the horizontal plane, planar grid, consists in subdividing in a grid of 16 by 16 in our case, the plan of this sail vault. Then we can obtain the intrados and extrados points by intersecting the vertical lines drawn starting from the planar grid, the intersection points of the planar grid, with the intrados and the extrados surfaces, as you can see in the figure. The method which is adopted builds upon the concept of force density by following the contribution by Sheck. Through this approach, it is possible to manage the equilibrium of antifunicular networks consisting of both unrestrained and restrained nodes, which connect a number of branches. The introduction of the force density vector allows formulating the equilibrium of the n unrestrained nodes as a set of linear equations. The force density vector stores the force to length ratios for all the branches of the spatial network. Without going in more details, the required input data are the planimetric coordinates of the nodes, the vertical limits for the height of the nodes, which we have obtained by intersecting the intrados and extrados surface by means of the straight lines conducted starting from the planar grid, the nodal loads, which we will examine more in detail after, and the connectivity between the elements. The optimization problem is then developed in terms of the vertical coordinates of the constraint nodes. It is formulated by following the contribution previously cited by Bruggi in terms of the reduced set of independent density forces calculated via a preliminary Gauss-Jordan elimination and solved by using sequential convex programming techniques. the constraint, for example, are that if we have the force density, the condition that they are less than 0 allows for enforcing that all the branches are subjected to compression, ensuring no tension behavior. And then the other constraint is given by the limits on the height of the nodes. It is to be observed that this implies considering in reality the approximation of the actual problem, because Feynman considers the line of resistance by considering the joints and the fact that the internal reaction cannot exit from the joints. In this case, we refer to the concept of line of pressure. So we have the nodes which are limited in this case. Obviously, we could extend the problem by considering also the actual stereotomy, not in this case. Another point is that we are examining by means of a technique which is framed within the limit analysis, a working condition. So we have to find the most suitable solution among the infinite one which are present. We are not in a convex condition. So we have following solutions recently developed in the literature. We have followed the principle of least pressure proposed first by Moseley, and we consider as an objective functions this one which extends to the 3 dimensions the principle of least pressure. We find a solution of minimum thrust. Okay. Then, to assign the loads to each node in the network, we proceed by constructing a secondary planar grid, dividing each segment of the original grid in half. Then we can consider the 3-dimensional model of the volt and section it using vertical planes drawn from the lines belonging to this new planar grid. In this way, irregular blocks with a quadrangular base are obtained. Then there is also the load of the infill. Such blocks, such loads have as a center of gravity a point which lies approximately along the straight lines conducted from the points of the first grid. We have considered different configuration of the network with increasing complexity. At first, a base configuration, which is a quadrangular grid. Then we have added the branches corresponding to the diagonals of the trapezoidal plane. And then we have added further branches starting from the vertices of the oculus and parallel to such diagonals branches. Then we have considered also configurations of the network which imply branches concentric to the octagonal oculus, and finally branches corresponding to the diagonal of each quadrangular module. So we have found anti-equilateral networks of minimum thrust corresponding to each of such networks. Obviously, computation time required for the complete analysis vary according to the grid. In this case, it is less than 1 minute, according to the technical details you can see here below. Here we have 1 hour and 45 minutes if we add the diagonal branches. Here the time increases to 3 hours and 47 minutes. And here we have 5 hours and 42 minutes up to the maximum timing, which is 21 hours and 12 minutes. In order to understand which one of such solutions was the most suitable one, parallel, we have conducted a finite element analysis by means of the Abacus software, modeling simply masonry as an isotropic linear elastic material. So the volt was discretized into quadratic tetraedral finite elements. We have assumed tangent boundary conditions, and we have imposed the self weight and also the load from the infill as a surface traction. Here you can see the results obtained by means of the finite element analysis in terms of minimum principal stresses, circumferential stresses, and meridional stresses. So we can observe that the more complex configurations are the more suitable to describe the behavior of this bolt, this irregular bolt. The domed portion near the octagonal oculus is subjected to compressive stresses. It is visible in particular in the second network below. But instead, we observe that the compressive forces increase near the side walls, as indicated in the first network by the blue branches. So this is interesting because it seems that such network configuration is more suitable to describe the behavior of the bolt, because this is also present in the graphical of meridional stresses obtained by means of the finite element analysis. The shape of the compressive step is consistent with quasi-circumferential forces. So if we conclude, the most important thing to observe is that funicular analysis and finite element analysis belong to different theoretical frameworks. But if we consider minimum closed solutions, we find suitable solutions, because we find a way to assess the working condition of the bolt. Obviously, from the theoretical point of view, this point should be further developed, because obviously in limit analysis we can only assess one of the infinite many solutions which we have. And also it has been interesting to increase the complex network configurations to verify the suitability of one shape or another shape network to the peculiar shape of the bolt. Further investigation are needed to fully interpret the real crack pattern observed in the bolt. Thank you for your attention.
Thank you, Danila, for this very nice presentation. So, any question, even remotely? Here?
No, I have just a curiosity. If I understand correctly, here in the finite element approach you have used, so abacus and so on, you model, you have done only a linear elastic analysis, correct?
Yeah.
Okay. And are you planning to perform even more sophisticated analysis?
And actually, for this peculiar bolt, we observed that tensile stresses were negligible. And so, in this peculiar case, the solution is acceptable. Obviously, if more complex shapes or different shapes, which imply the occurrence of tensile stresses, we could adopt, for example, a CDP model and so on. Yes.
A concrete damage plasticity, or yes. Okay, thank you.
I have just a quick question, and is how then the solution, the optimization solution, is how much is sensitive to the grid refinement? Because you have shown there then a medium refinement, and what's happening? I was wondering what's happening if you double then the number of node points.
Yeah, so now this information should be a little searched, because there is a sensitivity in terms of the solution, because
It's 5 hours, 6 hours basically of optimization.
Yeah.
It's quite a lot for a medium refinement like that one.
Yeah.
So I was wondering then also accompanying them my previous question, then if it is possible then to enforce then a number of nodes that is bigger, in order then to show if then the result is stable or not.
Yeah, obviously this is a question to be developed further in this research. But I can say that there is sensitivity both to the, as regards to the typology of grid which is considered. There is also a different, if we consider this grid, which implies having concentric branches, in this case, the fact that the result provides that the corners are less stressed implies that obviously we have another type of a different thrust with respect to this one, where we have instead that the corners are stressed. And so, yes, point by point along the perimeter, we have a stronger sensitivity. But it is interesting to observe that it is not true that by increasing the refinement, we improve the capacity to describing the actual behavior of the boat in terms of minimum thrust pollution, because this medium refiner is better than this one, according to a comparison with the limit analysis, which provides, for example, for meridional stresses that corners have less stresses. Yes, obviously we can also discuss this later, but as a general idea, this is the question.
Thank you very much.
Okay.
Thank you very much.
So the next presenter is Gabriele Milani. You will present a paper titled "The Limit Analysis of Irregular Measuring with Rigid and Deformable Blocks," co-authored with Yaroun Hermans, Yue Hua, Karim Ayab Mustafa Kamel, and Thierry Massart. Please, Gabriele, the floor is yours. I'm sorry if I don't know for the pronunciation of your co-authors, everything is okay.
I will specify to the audience that is very interesting information. Thank you very much. Yes, so maybe I can also activate the laser pointer. Yes, I am presenting them very quickly. Then I would like to apologize for the previous problem, so we try to be super fast. But this work that is some years that we are developing in cooperation with the Free University of Brussels in Belgium, with our colleagues Professor Massart and Karim Kamel. Basically, then the idea was developed and practically by our common PhD student that we have in Computational, that is Yaroun Hermans, with in collaboration also with my postdoctoral research at Yue Hua, that helped a lot then in the limit analysis implementation. But the idea is visible then from this first slide, from the introduction, that is that imagine that you have an irregular texture, and imagine that you take a photo of the irregular texture and you want then to digitalize the texture to make it to obtain a restitution then in vectorial form. And then there is a numerical model that allows you then to expand the blocks in order to use rigid infinitely resistant blocks in interfaces in limit analysis within homogenization using the representative element of volume, or then to return back and to take into consideration the actual thickness of the joints. So the idea is this one. So imagine that you have an irregular texture, you take a picture, and then so you have an acquisition that is classic, and then you have a segmentation. That means that you make it vectorial. And then there is a computational algorithm that we have presented then in a series then of previous publications that allows us with then this methodology that is based on setting up, so defined with some distance fields to find some medial axes of the mortal joints, because typically in such kind of irregular texture we have thick mortar joints with a thickness that is not constant. And then you can obtain this methodology, then an assemblage of blocks that interact with mortar joints that are reduced to interfaces, where this irregular texture is directly lumped into then the information that you give to the interface. Then you can use then a classic homogenization on the representative element of volume and limit analysis in order to find then the strength of such kind of irregular texture along different directional or along or under the application of different loading conditions. And then so you obtain also the formed shapes at collapse and also the overall homogenized strength. But we will see during the presentation that we are facing then this methodology with some problems. So the computational approach then to reduce then the thickness, to lump the thickness of the irregular joints to interfaces is basically constituted by 4 steps. The first is to identify tripole points. Tripole points are specific geometric points inside the mortar joint that are characterized by the intersection of at least 3 different typologies of joints. So are knots that are important to identify automatically. But then, having identified automatically such joints, you can connect then the joints and find then the interfaces that represent mortar joints. And you connect them with straight lines, and then you discretize then the interface with some interface elements, limit analysis, and then you correct once again. So you discretize, and then you correct once again then the shape then of the mortar joint reducing to interfaces, then according then to an algorithm that is fully automatic. To do so, we introduce then the concept of distance fields. So there is a first distance field that is a function that we call the dn1 that can be negative if then the point is inside a block, or can be positive if the point is outside the block. And this is basically then the minimum distance between the point and the surface of the block. And a second distance field that is called dn2 that takes into consideration then not the first block, so the block that is the nearest with respect to the point that you are considering, but the second one. So is a new function that in this case is always positive, because if you take into consideration one point that is inside the first block, then its distance with respect to the second block is always positive. And in this way, then you obtain these color maps. So you obtain in this specific case that is taken as benchmark that dn1 can be negative and positive, and dn2 is always positive. Why we defined such kind of functions? Because we want then to obtain this further function that is called OV. OV is just the difference between the previously then introduced two functions, so is dn2 minus dn1. In this manner, then we are looking for the 0 levels of such new function. So in this manner, so we obtain then the color map that you can see then this slide on the bottom right, because this function has a property that exhibits some 0 points, and the 0 points represent then the first step then to identify then the middle points of the irregular joints. So in this manner, we are able then to identify also the tripole junction points, simply then finding that points that nullify the different OV functions. So if you take into consideration 3 blocks, for instance, for this point, this block, and this block, then you have to look at the 0 points that contemporarily occur for the OV function for this block in this block, the OV function for this block in this block, and the OV function for this block in this block. So in this manner, then iteratively, then you are able then to find the 0 point and solve the triple joint. Having at disposal the triple joint simply then all automatic with an automatic approach, an approach that is handled fully automatically, then you connect with straight lines, so with segments, the neighboring triple points, in order to identify roughly then the join reduced to an interface. So as you can see then from this picture, then this straight segment, this straight line doesn't represent at all then the shape of this regular join, but can be corrected again, then having a look into, so minimizing then the distance of the discretization with respect to the OV function that represents the function that takes into account this block and this block. And for the other joints, then the procedure then is repeated automatically. Just to give you an example very quickly, then this was then the original then arrangement, irregular arrangement of the blocks. This is the identification, then this picture on the left gives you the identification of the triple points with the straight segments then connecting neighboring triple points. And this is the last step when you correct then the shape of the joints reduced interfaces, once again using OV functions. We have combined then this approach that is fully automatic with the kinematic limit analysis. So it's an upper bound that assumes then classically that the materials are rigid, perfectly plastic. In such case, then the interfaces, you then assume a certain yield criterion for the motor joints reduced to interfaces. For instance, then a Coulomb failure criterion with the tension cutoff and capping compression. We assume also classic plasticity theorems, so that hold for classic limit analysis, so an associated flow. And then we use then at the beginning then the assumption that the blocks are rigid, infinitely resistant. And then pretty soon then we then removed such hypothesis because blocks cannot be considered rigid, infinitely resistant, because the results that you obtain are very inaccurate. That's the reason why then a development that we implemented then recently in the last few years is that to add a certain homogeneous strain rate inside the blocks in order to take into account in an approximate way the plasticity that can occur also inside the blocks. And it's very simple because you add for each block 3 independent and then strain rate variables that can potentially take into consideration then the plastic dissipation that can occur inside the blocks. So the implementation is pretty simple, but because you have dissipation inside the interfaces. For the interfaces, then you can abandon then a linearization, so you can abandon the failure of the strand domain, and we did because it's more efficient. So instead of linearizing the failure surface, then we use a direct conic programming, in particular second order conic programming that doesn't require then the linearization of the failure surface, and then plus you have the dissipation inside the bulk of the blocks that are not infinitely resistant anymore. Okay, so the limit analysis, the finite elements that we have, and the different typologies of discretizations that we can have contains then a broad blend of solutions. So we can have rigid blocks that I have represented in this slide with this symbol. And so we have plastic dissipation that is occurring exclusively at the interfaces between contiguous elements. And then we can have also the bulk dissipation, and introducing them according then to the simplified approach that I have discussed in the previous slide. We have an approach that takes into account also the dissipation inside then the elements. Can be on the case that the morpho joints are used to interfaces is exclusively done inside the bricks, the blocks. And we are speaking about a continuum, in this case, finite element limit analysis, and then we have a combination of the previous then two finite element models. So dissipation at the interfaces between contiguous elements and dissipation also inside the block. Obviously, if we want then to analyze a representative element of volumes and we want to combine homogenization theory with limit analysis, we have a further problem because classical homogenization theory holds then rigorously only for a regular assemblage of blocks. And this is not the case for irregular textures. So that's the reason why recently then in our publication then we proposed a variation of the homogenization of a rigorous homogenization approach in limit analysis that introduces new knots basically at the boundaries and imposes further multi-point constraints. I don't want to go into the details then of this theory, but it works for irregular textures, and because I don't have time then to go deepen the discussion then into this intricate problem from a mathematical point of view. Here I would like only to show you some results, so a small sample of the results that we obtain in case that we take into consideration that the plastic dissipation inside the bulk and also the dissipation at the interfaces, where the geometry is simplified, lumping then the thickness of the irregular joints into the interfaces between contiguous blocks. Then the loading condition, just for the sake of example, is this one that you can see on the top right. Is pretty complex because you have compression, vertical compression, horizontal compression, and you have also shear applied. These two pictures then show the former shapes of collapse obtained and applied such loads, and the dissipation, plastic dissipation occurring then at the interfaces, so inside morpho joints that reduced to interfaces. This one then is the dissipation that is occurring in the bulk, so inside the blocks that are assumed. Remember you that they are not anymore rigid infinitely consistent. The reason that we want to put the dissipation then inside the bulk of the blocks is because we want to analyze what's happening then to such representative element of volume in a state of stress that is mainly compression. But as you can see, then we have cracks that are occurring then inside the interfaces, plus also dissipation inside the bulk of the blocks. The problem here is that if you reduce then to the joints, then to interfaces within then the homogenization that I have quickly reviewed then in my previous slides, couple of slides, you can see that the constraints that you put at the boundaries then are responsible then for a concentration then of deformation, so plastic deformation near the boundary, near the corners, and this is a consequence, a combined consequence of the irregularity of the assemblage of the texture, plus then the reduction of the joints to interfaces, because then the model doesn't have any more than the possibility then to make an average of the plastic dissipation that is occurring in the thick joints. So that's the reason why very recently then we returned back then with a discretization of the actual thickness of the joints for some examples, and this is then a paper that we have just submitted then to a special issue of Professor Angelillo in Mechanica, and hopefully that is successful, is appreciated by the reviewers, and then we proposed many different models, so blocks infinitely resistant plus thick joints with dissipation at the interface between two mortar elements, two contiguous mortar elements, plus bulk dissipation inside the mortar. Then dissipation inside the interfaces a priori assumed inside the blocks, and the same then discretization for the mortar joints, and then bulk dissipation also inside the blocks. We will concentrate then the results that we obtained only for the last discretization, that is the most complex, and these are the results that we obtained then for unloading case of the application of a poor shear action then on that representative element of volume. As you can see, then the deformation, so the deformed shape at collapse, is very realistic. On the left, you can see the plastic dissipation inside the bulk. So in this case, you have plastic dissipation inside the bulk, means inside the bulk of the mortar elements, plus the dissipation inside the bulk of the block elements. As you can see here, it seems that the majority of the dissipation occurs inside the joints, obviously, as expected, but you can see that you have dissipation, some elements that are dissipating also then inside the bricks, the blocks, and this occurs mainly near the corners. So this model is able then to accommodate the constraints that are imposed using the homogenization theorem. Also, you can see here that you have a dissipation at the interface between contiguous elements, mainly inside the mortar joints, but also then inside the blocks. So it's a model very complex that takes into consideration basically many different mechanical aspects. The most important are the irregularity of the thickness of the mortar joints, the irregularity of the shape of the blocks and the texture, and finally then the constraints, the over constraints that are imposed and enforced by the homogenization theorem. So thank you very much. We accident to answer, despite the fact that I was not fast at all because it took 20 minutes. Sorry.
The investors?
It's a very quick, short curiosity. For just to, how long it takes from the to transform the geometry of a wall, like in this case, to something that is numerical, so the image processing?
Fully automatic is super fast. It's fully automatic. Maybe I don't know if I was able then to show you that then the procedure doesn't require any interaction with a human being. So you take a photo and then you run the analysis, and then you obtain then a discretization that you like. And so we have different typologies of discretization. All the procedure takes less than 10 minutes. For a representative element of volume like that one that I have shown in my last slide. But then you have automatically also the mesh, and then we take the mesh and then we make then the analysis, the limit analysis with second order conic programming. For that shear case, it took less than 1 minute, 56 seconds on a common level.
Thank you.
You're welcome. Thank you very much.
Thank you. So I think we can close the first section of this workshop, and how many minutes? 10 minutes.
10 minutes, right?
10 minutes, right?
Yeah, I think it's great.
Allora, vediamo tre speakers nella seconda. Prima per Giovanni, poi Stefano e Vittorio sono l'ultimo tempo.
Io sono
Perché non fate prima tipo in presenza?
Va bene, facciamo iniziare in presenza e poi lo tiriamo online.
Perché così
Sì.
credo che...
Va bene, sono
Mi spiace,
io la cosa più divertente che io
mi dispiace, però io avevo un caldo
una catena, no?
Allora, se facciamo quelle in presenza è una ed è la mia.
Una sola.
Però nel suo caso prende l'attrito che online che aumenta il
E adesso Pingari,
se partiamo con quelle in presenza faccio io.
fai tu e ci sei Pingaro, ok, e poi l'altro gli è in presenza, mancano in presenza.
No, su tutto
No, tutto online.
Sono 4 online. Lasciamo parlare online.
Io ho visto in letteratura spinta massima ti mettono calata,
alle 11, alle 10, guarda che non è una cattiva idea, perché se tu puoi il join da social del cellulare, quindi
Sembra una prova
noi facciamo tutti
sembra una prova la commissione, no?
ci dovremmo solo connettere alla sessione online, perché tu moderi online.
Esaminare anche le volte in esercizio e capire qual è la più
Andrea,
tu la vera
e a breve si collegherà anche se perché sai
cose lei la fa.
Perfetto,
Quindi in verità potrà ritirare Stefano da remoto.
Sì,
Stefano da remoto, esatto.
sì, tu ci vuoi dire che sono da remoto questo sì anche, cioè, insomma.
Noi le lasciamo
esiste la soluzione.
Sì, non c'è più presente.
Invece, nel caso della
Io inserisco, io già quindi strumento condivido, siamo online.
Dovrebbe avere la procedura
ci devi moderare voi lui.
perché così in teoria si deve fare questa informazione che quella corrispondente di fare la scuola dell'interno con una mano. Però questa soluzione non corrisponde alla spinta minima. Ragazzi, io sono qua fuori, più grande, cioè è più grande. E quindi il dubbio è, ma la volta lo sa, abbiamo rispondere tutti i servizi.
So, we are going to start the second part of our workshop, ANAPS. So the presenter of this work is Natalia Pingo, and she's going to present the work titled Nonlinear Analysis of Arches, a comparison among the three different methodologies applied to a multi-ring model. And this work is done in collaboration with Alessandro Gandolfi, Tua, Natalia Pingo, the presenter, and Gabriele Milano. Thanks, Natalia.
Thanks, Antonino, for the introduction. So, let us start seeing the outline of the presentation. So we will see the motivation and objective behind the research, then the three different approaches used to analyze a multi-ring masonry arch, namely an heterogeneous limit analysis approach, a finite element analysis employing elastic body and spring method procedure, and finally Femanola, which is a non-made finite element software specifically conceived for the structural analysis of in-plane masonry structures. Finally, we will see the results comparing the three different approaches, and at the end, I will draw some conclusions. So the stability of masonry arches is nowadays an open problem, and the importance of the investigation is straightforward and clear because arches represent the major assets of historical buildings in vulnerable countries. And in fact, diffused all over the world are collapses for the application of direct and indirect seismic excitation and for vertical loads in historical masonry structures. For these reasons, the analysis beyond the elastic limits are subjected to countless studies aimed at a sound consolidation. And nowadays, there are no sufficiently simple and predictive computational models able to provide information on the actual and future vulnerabilities, and so the proposal of simple models to put at disposal to both researchers and designers is a computational priority. I would like to highlight the picture reported in the right part of the slide, where there is the Treponti Bridge, which is a monumental bridge located in Comacchio in the province of Ferrara, and this drawing is taken from the Pallotta Canal, and the arch in the middle between the two towers is that analyzed using 3 different approaches. So here you can see the masonry arch, so a zoom of the previous picture, then discretized as multi-ring, and the objective of this work is that we want our structural tools to be simple, and we want that only few parameters are set in input in order to obtain a low computational demand. Our goal is to obtain an ultimate load capacity. The load displacement curve, obviously, only for what concerns the finite element analysis and not the limit analysis approach, and the progressive evolution of damage within this arch. So this approach will be accurate and simple enough, and it can be used for both academic and professional use. So it is our arch. You can see some geometrical characteristics. You can see that the springing are characterized by fixed connection. You will see the displacement applied more or less at 1/4 of the arch span in order to assess the behavior of this complex stereotomy, I would say, under the application of a concentrated vertical force. So the first methodology considered here is a heterogeneous limit analysis. In this approach, masonry is represented as an assemblage of rigid blocks connected by frictional interfaces governed by a Moore-Coulomb criterion with tension top. As shown on the right, the velocity jumps are computed at each interface, while the constitutive law defines the admissible stress domain. Under the associated flow rule, the upper bound and lower bound formulations become dual optimization problems, allowing the collapse load to be determined efficiently with a very limited computational cost. However, the associated flow rule introduces an unrealistic dilatancy effect, leading to an problem. Please, can you turn off the microphone? Okay. I would say the associated flow rule introduces an unrealistic dilatancy effect, which leads to an overestimation of the collapse load. To overcome this limitation, we adopt a sequential linear programming procedure, and starting from the associated solution, the algorithm progressively reduces the friction angle and updates the cohesion so that the yield surface passes through the previous test state. The optimization problem is then solved again, and the process is repeated until convergence, providing a more realistic prediction with zero dilatancy. Here, it is possible to see the finite element approach adopted in a standard finite element software, namely Strauss 7. Here, the blocks are modeled using elastic 8-noded elements, whereas all the nonlinear behavior is lumped at the interface. These interfaces are modeled using trans elements, in particular point contact, which behaves as linear elastic, and then in the inelastic range, perfectly fragile. The only parameters that we need to set in input are basically the elastic modulus of the joints, the influence area of these classes, and the tensile strength of mortar joints. Finally, the third approach consists of Femanola, which stands for Finite Element Measuring Nonlinear Analysis, and Femanola is a new developed in-house nonlinear static finite element software which employs a fully explicit iterative elastic scheme to handle material non-linearity. Mortal joints are modeled using 4-node isoparametric elements with the normal stiffness in the joint direction set to 0. The joints can be either meshed with their real thickness or with a negligible one in order to simulate dry joints, as in a standard heterogeneous discretization. The problem is based on plane stress assumptions, though can handle also plane strain problems. The element stiffness matrix is written in a standard way, where D represents the elastic stiffness of mortal joint, J denotes the Jacobian of the transformation from physical to natural coordinates, B is the matrix of the first derivatives of the shape function, and finally a rotation R is applied to transform the element stiffness matrix into the global coordinate system. As far as the nonlinear behavior is concerned, its general features are shown in the picture reported here in the bottom part of the slide, which specifically illustrate the penalization strategy applied to elastic and shear moduli at a Gauss point experiencing softening in under tension, the picture on the right, and shear, the picture on the left of the slide. So let us see now some results. Here the associated limit analysis results are presented. The material properties and the parameters adopted for the sequential linear programming procedure are reported on the left, while the predicted collapse mechanism is shown on the right. The analysis identifies the classical 4-hinge mechanism, but it also exhibits significant ring sliding accompanied by spurious dilatancy. As a consequence, the associated formulation predicts a relatively high collapse load of about 228 kN, highlighting the tendency of this approach to overestimate the structural capacity. When the non-associated flow rule is adopted, the collapse mechanism becomes much more realistic. The artificial dilatancy is significantly reduced, while the characteristic 4-hinge mechanism is still correctly captured. As expected, this also leads to a lower collapse load, around 186 kN, which is much closer to the prediction obtained with the finite element models we will see from the next slide. And this confirms the importance of considering a non-associated flow rule when analyzing multi-ring masonry arches. Here are the results obtained from Femanola, so the homemade finite element software. Here it is possible to see the deformed shape found more or less at the middle of the analysis. The analysis is incremental from the first step to step 50, so middle of the analysis step 25, and the last step of the analysis step 50. First, in this analysis, we assume a finite shear strength. In fact, it is possible to notice sliding more or less in the in correspondence of the application of the applied force. And here, instead, we assume, let's say, an almost infinite shear strength. And in fact, here, the behavior of the arch turns back to the hypothesis of the formation of flexural hinges. Let us see now the comparison between these different approaches. So what we can see is that the limit analysis associated exhibits, so this line here, exhibits the highest collapse loads. Then we have the result from Femanola with, let's say, an almost infinite shear strength. Then Femanola again with a finite shear strength. Almost, we found the same value with the limit analysis non-associated. And then we have the results obtained using the elastic body and spring method approach developed within a commercial finite element software. The zigzagging behavior that we can see in the finite element curve is due to the failure of the trusses, which face, as I said before, fragile, and so this zigzagging is due by the failure of some point contacts during the incremental analysis. And here instead we see the deformed shape at collapse found with the commercial fine intelligent software. So to conclude this work, the associated limit analysis overestimates the capacity. The non-associated one is closer to the results found with fine intelligent models. However, limit analysis is the fastest method, but it cannot provide us results regarding and information regarding displacements, which is nowadays a very important feature, especially if we are dealing with displacement-based design. Whereas information regarding the progressive damage evolution are easily obtained thanks to both Femanola software better but also with an elastic body and spring method approach. Another thing that I would like to highlight is that Femanola, so an homemade fine intelligent software, is much faster than a standard fine intelligent software. If you look at here, with Strauss 7, so endpoint contact, we use 38 minutes with a standard laptop, whereas Femanola 4 minutes with a standard laptop. So the difference is enormous. Obviously, limit analysis is the faster because 0.03 minutes. But with the other approach, we can have information also regarding displacement, regarding the evolution of damage and so on. And that's it. Oh, no, sorry, here are some references used to carry out the work. And that's it. So thank you so much for your attention.
Thank you, Natalia. Is there any question you would like?
Can I? Only a curiosity. When you have these different layers in the art, and we consider the mechanism, it happens that, if I have correctly understood, sometimes a single block falls down because there is a detachment.
Slide. Yeah.
Not only sliding, also lack of transmission between the compressive forces.
Ah, okay. I get here, you mean, right?
Yeah. Yeah.
Okay. Yes. Yes.
It is quite interesting and non-typical in limit analysis because we assume always that the blocks are in contact. So you introduce a new
wait, this screenshot is taken from the fine intelligent software.
Yeah.
So not from the limit analysis result.
Okay. Yeah.
Here, this let's say how to say, like that the block seems flighting.
Yeah.
Is due to the fact that we use normal point contact elements. Once we reach their ultimate, let's say, resistance, they do not sustain anymore the load or whatever you are applying. So basically here is just this block loses completely the interfaces, loses completely the resistance, and so this strange deformation is simply due by how to say, by the fact that these point contacts are not working anymore in the software.
Yeah, but I think it is compatible with the true mechanism.
May I add
Yes,
something?
sure.
This one, that picture that you see over there is, as correctly stated by Natalia, is with point contacts. The point contacts exhibit a certain tensile strength.
Yeah.
So from the deformed shape is low, but it's not zero. From the deformed shape, you can say that the point contact is not transmitting anymore tensile strength because when you implement the point contact beside the commercial code Strauss 7 has a certain thickness, that is the thickness of the joint. So what you see there is only then the boundary of the block but you cannot say that is not able to transmit the tensile stress.
Here, it is not because the plot from the screenshot, the beam element, the truss elements are removed. But here, in reality, you have point contact here, point contact here, point contact. Oh my God. Okay, in any case, useful point contact. No, doesn't work anymore. Okay, I was saying that also here from this corner to this one, you have another right, where we have now the red point.
Transmit stress message.
Yes, exactly.
You cannot say anything on substrate body shape.
No, no.
Should investigate more than determine cause.
Yeah.
But if there is still in equilibrium, then it seems that then that block can be in equilibrium, but it can because there are some classes that are connected, that are linking at the interface level.
Okay, in the model, yes, but okay, because of the modeling, it could be also an hypothesis to extend by considering such
possibility. Yeah.
Because I think it could be quite clear.
Any other questions?
No. Thank you, Natalia. So now we have four remote presentations, online presentation, but see that point of
Forse
non riesco a chiudere.
PowerPoint non si riesce a fare. Ma è il tuo? Di
Natale.
Ok.
Sì, ora non vedo, iniziare con le 4 presentazioni online.
Perfetto.
May I ask for the people who are online to mute your microphone? Just
Ok. Perfetto. Quindi, adesso sono solo presentazioni online.
so we have only 4 online presentations. I would say that maybe Andrea, if you want, you can.
Okay. Okay. So thank you all. We start the full remote workshop. I will share the session. From now on we have 4 more presentations. The first one is by Lino Cusano with title VEDEM Plus, Enhancing the Engineering Assessment of Complex Steratomic Structures via 3D to CAD Post-Processing Workflows. So Lino, please share your screen. Okay.
Okay. Can you see the screen?
Yes, you can go.
Okay. Thank you, Professor Montanino. Good afternoon, everyone. My name is Lino Cusano, and I recently completed my master's in civil engineering at University of Sannio. And I'm presenting this joint work with my supervisor, Professor Antonino Iannuzzo. In this presentation, I'm going to illustrate VEDEM Plus, a 3D to CAD post-processing plugin for the engineering assessment of complex steratomic structures. This work is part of my master's thesis, and that focuses on the steratomic flat vault modeled with 3D by Raska. And during my study, a clear problem emerged. 3D is powerful software, but extracting engineering insight from its output is slow and quite challenging. So it needs a lot of manual work. So VEDEM Plus was developed to try to solve this problem. So a quick overview of the outline. I would start with the motivation, and then I will move to the reference case study. And then I will go deeper and focus on the pattern pipeline and architecture and how it's built, so with the visualization modules. And then I will show you a quick overview of the application to the case study, and then we'll move to the conclusions. So as for the motivation, a DEM analysis in general on a large structure, so made of a lot of blocks, like a mesonet structure, means that there could be a lot of tens or hundreds of loading steps, for example, and each of them producing block positions or velocities, a lot of information and output data that it's complete, but actually turning it into something that is easily visible, it's quite hard. So we can address three problems. The first one, as I was saying, that is the volume of the raw output. So that makes a manual inspection unfeasible, or I would say hard. And also, the second problem is that the 3DEX native visualizer is not built for an interactive exploration. And the third problem is that if we want to assemble, for example, the force path or force displacement curves from the raw data, it requires a lot of manual scripting. So this is the gap that DEM Plus is trying to close. As for the reference case study, before I describe the tool itself, we are talking about a steratomic flat bolt that is actually an historic typology where all the loads are carried only in compression, in pre-compression. So this kind of structure are dry assembled without any reinforcement. And they are also demanding because they present large horizontal thrust and also kind of covered sliding and hinging collapse mechanism. So, and they also are very sensitive to the geometry of the joints and the support displacement. The vault that I studied here, it's a simplified model of the real construction, the real structure that was built in Spain by Mas Piedra and designed by the professor Enrique Rabasa. In this slide, on the left, we can see the non-convex blocks with the geometry that, I mean, we needed to disassemble and reassemble with sub blocks, convex blocks, because the 3DEX contact detection operates only with convex polyhedra. So as we can see in the center of the slide, the model was divided in 4 families, divided by color, of non-convex blocks that were first disassembled and then assembled as convex blocks. On the right, we can see the schematic of the displacement controlled analysis. So the 4 supports were displaced outward symmetrically, and we tracked the structural response step by step until the collapse. As for the pipeline and the architecture of this tool, the workflow has 3 main stages. First, the geometry is built parametrically in a kite environment. In this case, we used Rhinoceros 8, and where as I was saying before, all the non-convex blocks were reelaborated, so decomposed and then into convex sub-blocks. Then the 3DEX analysis ran the incremental test, and at each step, a custom fish script that we developed specifically for this study that export the geometry, the contact information, and the penetration information as JSON files. And then all these outputs are important again in Rhino through Venom, so we can start the post-processing. This is a short video of the plugin in action. Venom Plus, as you can see, is a dockable panel and is that communicates in real time with the 3D viewport in Rhino. So every tab covers all the information that we exported from 3DEX. So we can study and the blocks part. So we can understand the geometry. We can interrogate about the contacts. So how the forces are moving around inside the geometry, and everything is linked to a step slider, so we can understand step by step what is happening at our geometry. And so every step can be toggled on and off, and so we can make a real-time comparison between different steps. So as for the architecture of the plugin, Velen Plus was written in C#, and it was organized in 4 clean layers. We have the data models, the JSON loader, the visualizer, and the user interface panel. We decided to use this structure because in this way we can modify or improve and implement new parts in this plugin without touching the core of the plugin. And we decided to use the C# language over the Python because it works better, we have better performances with the larger data set as we are working with. So as for the visualization models, we have 4 models. The first one renders the deformed geometry of the assembly, and each block is represented with a triangulated mesh, and it can be colored by any scalar field that is available from the output from 3D. So we can use the displacement components or the velocity or the unbalanced forces and etc. There is a blue to red palette that is normalized to the current step that we are analyzing, and so we can see different colors to understand better what is happening during our analysis. So the engineering value here is twofold because the displacement field, for example, immediately shows which side is moving and by how much as the supported displacement is incremented. And because all the geometry is organized under a layered hierarchy, it's possible to make a comparison between different steps in real time. Here is an example of what we can do with Velen Plus. In this case, we are looking at a displacement chart for one step. And so, as you can see, it's very easy to have like at least a visual check that if we want to take it from 3D, needs a lot of manual work. The second module addresses the force path through the joint network. So at the contact level, the plugin calculates and draws all the normal force, the tangential force, and also the resultants. And it draws the scalar vectors that they are anchored to the center of pressure of each interface. The center of pressure is optionally rendered as a sphere, so it gives an immediate reading of where within the joint space the resultant is applied. And also there is an option to show the torque, if it's present, that is represented as a circle in the contact plane. At subcontact level, we can have for each contact point, we can understand the state of that contact. So we can have an immediate failure map. So we can understand if we are sleeping or it's opening. Here you can see the contact force visualization for the Volt assembly. The green lines represent the resultant forces during this step. And so we can easily understand the 3D arching behavior of this assembly. So the forces are channeled along diagonal paths through along from the loader region, sorry, toward the supports. So this kind of behavior is typical for this geometry. And thanks to Velen Plus, it's easily readable. So we can have a direct visualization of the stretch path inside the geometry. And this is not available in TDEC, a direct tool like this. So the third module tracks the joint opening and closing across the loading segments. So for each subcontact, the normal gap is calculated as the initial aperture plus the accumulated normal displacement. And a negative gap means that the contact is closed and it's loaded, while a positive gap means that the joint is opening. So each subcontact is calculated and rendered as a flat circular disk that is oriented with its axis parallel to the contact normal. And plus, there is the option to have a threshold filter that suppresses some contacts below a user-defined value that allow us to reduce some numerical noise. So the engineering value here is the ability to track the sequence of the joint opening step by step. So we can see in real time what is happening, which interface is opening first, and which order the distribution of the forces follows. And plus, we can understand where the compression concentrates while the structure approaches the collapse. As I was saying, for this kind of analysis in them models, the contact between blocks produce a small geometric overlap. So we, exporting the geometry, we exported also this data about the overlapping using another script, a fish script. So we were able to reconstruct the actual surface, contact surface, and so the pressure surface. And of course, using Venom Plus. And this is another thing that is not natively provided in 3D, especially for complex geometry, especially for complex geometries. So this was used to create, we call it the gap mapping on the geometry. So this can show in a direct way what is happening. So the formation of the hinges and of course that how it changed during the analysis. So as long as the displacement is increasing. The fourth and the most analytical module is the one that provides a per contact force history across all the loaded steps. So we can select an interface from the geometry direct on Rhino, and we will have a detailed dialog that shows 4 synchronized charts. One is for the normal force, one is for the tangential force, one is for the combination, so we have the resultant. And another one is for the friction ratio that it's linked to the Moore Coulomb threshold. So we can understand the friction angle directly from the output from 3D. And also we can even change it. We have an override function, so we can re-render in real time what happens if we change the friction angle. Of course, all the data that we can collect with Venom can be exported usually in a CSV. So we can have for each interface, for each step, for each contact, all the information that's coming out from the 3D. So as we're saying, all the resultants, all the coordinate of the vertex, etc. Here is an example of what I was saying about the interface. So we can understand how the geometry is working, and for each contact that we select for each interface, we can understand what is happening. On the bottom right, we can see the friction ratio chart. That it's very important because when the force path approach the threshold and touch the threshold, it means that the sliding is happening in that step for that interface. So it's a quite important thing that we can see here. And as for the application to the flat vault, the analysis that we carried out in 3D was an incremental displacement controlled test. So as I was saying before, we displaced upward symmetrically the supports of 1 millimeter per step. And then we use Venom Plus to interpret all the results. So the block geometry that we exported on the first step allow us to visualize the deformed shape of the assembly for each step, so for each settlement increment. And so we had like an immediate physical consistency check. Plus, with the subcontact force maps, we were able to understand the evolution of the internal force distribution. So, of course, step by step. And so this allowed us to understand, selecting all the joints, selecting some joints to understand the hinge formation. And the gap map allowed us to follow, to identify the sequence of the joint opening. So this kind of tool, it's very precious in my opinion. So we can have a direct visualization of what is happening during this kind of analysis. So this slide is an example of an analysis that we carried out for one contact. And on the top left, we can see the resultant forces inside the geometry. And the bottom left, we can see the penetration map. And as I was saying before, with all this chart, we can study all the force part. So this is the kind of engineering reading that Veren Plus can make directly accessible. As for the conclusion, to summarize, so Veren is kind of a bridge between the 3D solver and the CAD environment using the JSON-based pipeline. So we can have a fully controllable CAD post-processing environment. All the models that we developed were in direct response of what were our needs during the study of this board. And of course, this tool is not perfect. We still have some limitation, like the lack of zone level stress visualization, or we had some problem with bigger data set. But we are already working to address these problems. And also, we are trying to develop a standalone viewer independent from any CAD platform. Thank you for attention, and I'm happy to take any questions. Thank you.
Okay, thank you, Lino, for your interesting presentation. There is a short time for questions, if anyone from the audience. If there is no question, I thank again Lino and go to my presentation. So I will share the screen. Okay, can you confirm that you see my screen? Sorry?
Yes, you can see it.
Okay, thank you. So I am Andrea Montanino, and I'm going to present this work prepared together with Francesco Fabrosino. The work is entitled The Task Method for the Design of Supporting Structures. The outline of this presentation is shown here. I will first present some modeling strategies for masonry structures, and then I go to continuous models. And in particular, I will introduce the CAS discretization method. And finally, I will show how to adopt the CAS method as a design tool for masonry, for supporting structures. Masonry, as we know, is a particular material whose deformation is concentrated on blocks interfaces, while blocks can be, in theory, considered as rigid, and the sliding usually is not allowed between blocks. This calls for a block-based computational model of masonry structure, and most important tool for this tool for modeling the masonry structure is the distinct element method. But from observation, we see that structure develops also on the interior of blocks and not only at the interfaces. Therefore, moreover, the discretization adopting the real number of blocks of a huge masonry wall would be particularly prohibitive from a computational perspective. Therefore, we would like to go to continuous model for masonry structure. Therefore, here you can see the continuous version of the boundary value problem for masonry structure, questions of equilibrium and kinematics, both of the interior and of the boundary of a structure, in which we add the Hyman hypothesis for masonry structure that translate into mathematics what we have defined earlier. So stress can be only compressive, deformation can be only in opening, and no sliding and no dissipation is allowed. In particular, a triplet of stress, deformation, and displacement is a solution if, of course, all constraints are fulfilled. This same problem can be translated into a variational formulation by introducing two different potentials, total potential energy, in which the unknown function is the displacement, and the total complementary energy, which depend on the stress function. Again, T0 is 0 and U0 as a triplet is a solution of the boundary value problem if they simultaneously represent a minimum for both the total potential energy and the total complementary energy. Focusing on the total complementary energy, we want to derive a force-based approach. So the strategy is to try to minimize the total complementary energy under the condition of equilibrium on the interior, the equilibrium at the boundary, and material admissibility. These three conditions together represent the set H of admissible stresses. One way to simplify the problem is to introduce the eddy stress potential that is a scalar function whose second derivative represent the stresses. Adopting this potential, the internal equilibrium is automatically satisfied. This contributes to reduce the number of constraints of the eddy stress potential of the boundary value problem. In this, by adopting the stress potential, we can demonstrate that the negative semi-definiteness of the stress is translated into the requirement of concavity of the eddy stress potential. So the boundary value problem can be reformulated in the minimization of a total complementary energy that depends on the eddy stress potential in the set of admissible eddy stress potential, which is defined as the internal equilibrium is automatically satisfied. The boundary equilibrium translates into conditions at the boundary for the eddy stress potential and its normal derivative. And the material constraints is translating from a condition of negative semi-definiteness of the stress into the concavity requirement of the eddy stress potential. So now I'm going to introduce the CAS method, that is the continuous eddy-based for stress singularities method, that is a force-based computational approach for the equilibrium solution of unilateral material. The discretization strategies of the CAS method consist in adopting a plate type finite element method, or finite element discretization, whose nodal unknowns are the eddy stress potential and its Cartesian derivatives at each node. So the method is a C1 is C1 continuous across element, meaning that we approximate the eddy stress function through regular functions. But this approximation does not ensure the continuity of second derivatives at nodes that, as we can remember, represent the stress. So stress are not defined at nodes. So we calculate them on internal points of the domain. And so we can check the material admissibility constraints on internal nodes of the elements. The method has been extended to generally shaped quadrilateral elements through a mapping between a parent element and the real geometry of the elements. And so we can reformulate finally the problem as the minimization of a discrete complementary energy in the set of discretized eddy stress potential, in which the boundary equilibrium is represented by equality, a system of equations, and material constraints is represented by a set of conic inequality constraints. This boundary value problem presents multiple stress solutions for equivalent minimum objective function. So to know different possible stress potential, one idea is to modify the setting function, that is to modify the displacement boundary condition in the domain. So in this way, we can try to observe many possible stress patterns that can develop in stress structure. Let's consider this example. We have a portal, and we want to design a supporting structure, for example, a flying buttress on the side. To do this, we need to know which is the emerging stress on the side of the portal on the red region. So to know all possible stress that can develop here, we can change the boundary condition on a part of the domain. For example, we can rotate this left support for a full angle, and so in this way we can know many stress distribution and traction that may develop here on this side. For example, quick settlement angle, in this case for a 0, 90, 180, and 360 degrees, we can see 4 different stress patterns and consequently different regions, different stresses at the selected interface. We represent here for these 4 angles 4 different sigma distributions and tau distribution on the region in which we are interested. But for many more angles, from 0 to a full angle, we can collect all possible couples of horizontal direction and vertical direction on the region S. And therefore, we can use this diagram as representative of all possible reaction forces that can develop on the region on which we want to build our supporting structures, on the basis of which we can design our supporting structure. So we know that when we want to design the supporting structure, the range of the forces that can develop is comprised inside this red curve. So in this presentation, I have recorded the Amen's assumption for measuring structure and the fundamentals of the CAS methods. And finally, I presented an application, a possible application of the CAS method to the design of supporting structures, structure based on the span of possible stress pattern that can develop inside a structure. So thank you for your attention. I'm happy to welcome your questions. Is there any question from the audience? Okay. Well, so if there is no question, I will go to the next presentation, that is by Stefano Galassi. The work is authored by Stefano Galassi and Giacomo Tempesta. Is entitled Stability Analysis of Masonry Domes and Crack Interpretation through a 3D rigid block model with concentrated deformability. So please, Stefano.
Okay, thank you, Andrea, for introducing me. Just a moment. Can you see the presentation? Can you see the presentation, please?
Yes, you can go on.
Okay, thank you. Okay, my presentation concerns the stability analysis of masonry domes and crack interpretation through a three-dimensional rigid block model with concentrated deformability. Just to introduce this topic, I want to recall that historical building stock consists of masonry buildings which are characterized by typical architectural and structural elements such as arches, walls, domes, spiral stairs, and so on. And these components often have cracks. But cracking is a common occurrence in masonry structures given their very low tensile strength of the mortar joints used to build the masonry units. So it is necessary to determine the causes of damage to prevent local and global collapse. To this aim, reliable analysis methods are necessary. Now I want to propose a three-dimensional rigid block model with concentrated deformability to assess structural stability and predict the occurrence of cracking at the joints. This presentation focuses especially on domes, for the analysis of which methods based on graphic statics were developed in the past. I want just to recall two schools of thought, one in the 18th and one in the 19th century. The first one that considered the dome as an assemblage of individual arches. So the idea is that the behavior of the dome is the behavior of one-dimensional elements. The second school of thought in the 19th century instead assumed the behavior of the dome as two-dimensional. So there are forces along the parallels and the meridians. In particular, in the first school of thought, I want to recall Pierre Bouguer because he was the first to address both the topic of designing a new dome, the first question, and the verification of an existing dome, the second question. Regarding the first question, he was perfectly in line with the analysis of one-dimensional elements. But when he deals with the second question, he understands that the masonry dome has a two-dimensional behavior. So he anticipates, the second school of thought, that of the 19th century, which begins with the advent of the theory of elasticity. The most famous method developed in this period is the membrane theory devised by Eugenio Beltrami, and the membrane theory is commonly used to analyze masonry domes. But as you well know, the scenario of internal forces, the membrane forces, is generally not consistent with the one that a masonry dome can withstand, because it is not as thin as a membrane and has a very low tensile strength. Tensile forces cause the development of cracks along the meridians. The internal forces are no longer located in the middle surface of the dome, and the position of the neutral parallel is variable and depends on these aspects. Based on this reasoning, I introduce an intermediate school of thought that is that of Eddy and Levy, who understood that the behavior of the masonry dome is a mixed behavior between these two schools of thought. That is, there is a double behavior because tensile forces causes cracks along the meridian. So the behavior of the dome is subdivided into different parts. The upper part, which behaves like a membrane, like a shell, so it has a two-dimensional behavior, and the lower part, which is characterized by individual arches, so there is one-dimensional behavior. But all these methods have a common feature because they are based only on equilibrium. And then also thrust line methods are based on this. They were extended for the analysis of three-dimensional structures such as domes, and they became the thrust network methods of analysis. They were proposed by Dewey, then Bloch and Oxendorf, Marm and Rosati. The last contribution is from my friend Antonino Iannuzzo. But in this presentation, I want to discuss another kind of model which is based both on equilibrium and congruency. It is a rigid block model with concentrated elasticity, concentrated wear in the joints. So rigid blocks are obtained, are cut out between two adjacent meridians and parallels, and they are connected by meridian and parallel joints that act as thin elastic layers. The basic, I want to say so, reference joint is modeled as a discrete device composed of at least 4 links orthogonal to the middle surface to transfer the axial force, and 8 links in the plane surface of the joint to transfer the shear force. So there are 4 links in the parallel direction and 4 links along the meridian. Then this joint can also be refined, as you can see in the figure at the bottom on the right. But to obtain this three-dimensional model, we have to make a two-dimensional model that is the profile of the meridian. So we make planar rigid blocks which are connected each other by planar joints, and these joints are presented in this slide. The basic one on the left, in the middle of the slide, is composed of two axial links, N1 and 2, and 2 shear links, T1 and T2. But I can use a more refined joint, which is shown in figure B. Then we have to extrude this planar structure to obtain the three-dimensional model of the dome. And to do this, a computer program, Brickwork 2.0, has been developed to model the two-dimensional structure, to extrude it, to obtain the three-dimensional structure, and to compute, of course, the structure. What about the behavior of the joints? We have to define, of course, some strength criteria according to the behavior of masonry. On the left, you can see the strength criteria related to the axial links of the joint, that is compression and tension, and on the right, the strength criteria related to the shear links. As for the first one, we can define a threshold value for tension, which causes the failure of that link. So the behavior is linear elastic brittle. As for the links subject to compression, if I define a threshold value, it causes the yielding of that link. Instead, as for the shear links, if we define a threshold value, which is computed according to Coulomb, when the shear force in a link reaches this value, this link may fail, and so the behavior is brittle, but I can also choose to the plasticization. Of course, to analyze this discrete model of the dome, I have to write both the equilibrium and the congruency, that are the elastic kinematic equations, which are presented in the matrix equation 1, which are subject to the strength criteria in the inequalities in equation 2. The key point of this procedure is vector delta, which is in the elastic kinematic equation, which is the tool that I use to meet the strength criteria. Vector delta is composed of two portions, delta star and delta star star. The former is aimed to assure equilibrium, and the second one to ensure the compatibility. Okay, this vector is the distortion vector. So I introduce distortions into those links that whose forces do not meet the failure criteria or the strength criteria. These strength criteria imply, of course, nonlinear behavior of the masonry dome, and so a numerical procedure is developed. Solving, of course, matrix, the equation 1 subject to equation 2, we obtain the vector x of internal forces, equation 3, which is a vector composed of two portions, vector xo and vector x perpendicular. The first one is contains entries of vector x0 are the internal forces in the links caused by the forces in vector f. The second one, x perpendicular, is the vector of the inner forces in the links caused by the distortions delta star. The problem is this, that this equation provides vector x as a function of vector delta star, but vector delta star is an unknown as vector x. So we have an equation with two unknowns. To work around this problem, we have used a numerical technique that is this. We have rewritten equation 3 in the simple form of equation 4 that is the same. Then we have partitioned this equation, see equation 5. We have partitioned both vectors and matrices of equation 4 in order to isolate entries that meet, subscript B, the failure criteria, from those that do not, subscript C. We have obtained equation 5, and the solution of equation 5 provides both the distortion vector delta star, in particular the subvector delta C star, which is the vector of effective distortions, and then the solution vector xb, or vector x, xb, x, and t, which provides all the forces within the joint links that meet the failure criteria. The second phase of the analysis, of course, is related to the modified configuration. So we have to calculate the displacement of the blocks, the deformation of the joints, and the cracks along the joint. To do this, we consider the second equation, the elastic kinematic equation, but we have to solve this problem. We have again to partition matrices and vectors of this equation in such a way to isolate entries that meet from entries that do not meet the failure criteria. So we obtain equation 8, and the solution of this equation provides the vector of effective displacement of blocks and toroids, as well as vector delta C++, that is the distortion vector, aimed to restore compatibility. This means that this vector provides the width and the depth of the cracks in the mortar joints. Just to speak in terms, this vector is like some mortar that you put inside a joint which is cracked, too close to feel it. So it's like a wedge, and this wedge, the shape of this wedge, allows one to measure the cracks in this joint. This is vector delta C++. This method, this mechanical model, was used to analyze the Dome of Santa Maria del Fiore in Florence, which is a very famous dome in the world. This is an unusually shaped dome because it is a polygonal dome composed of 8 lunes that are segments of elliptical cylinders. The dome consists of 2 shells, one inner and one outer, which are separated by a cavity of 1.2 meters. These 2 shells are joined by a system of 24 meridian ribs and 10 parallel ribs. The geometrical data used to create the mechanical model were derived from the pioneering studies by Salvatore Di Pasquale, published in 1977. The geometrical data used are these: the radius of the diagonal rib is 36 meters, the inner and outer diameter 45 and 55 meters. The overall thickness comprised the cavity between the inner and outer shell is 4.5 meters. As you can see in the figure on the left, each lune of the dome is a portion of an elliptical cylinder. On the right, you can see both the plane of the plan of the dome, the octagonal plan, and then the cross section, the 2 cross sections of the dome. I want only to point out a particularity, a singularity of this dome, that the key aspect is that each quartz of brick lies on a conical surface. So the parallels, just to understand, are not parallels because they are curved. They are if I want to express then these parallels in mathematical form, I have to use an equation of 4 degrees because these surfaces are the intersection of elliptical cylinders and cones. Okay. Then we have modeled this dome starting from the 2-dimensional model. So we have modeled the parallel, the shape of the meridian of the circular rib, which is composed in our model of 2 parallel rows of 14 rigid blocks, which are connected by 2-dimensional devices comprising 2 axial and 2 shear links. Then we have generated the 3-dimensional model through the extrusion procedure. So we have extruded along a circular generatrix 8 times at 45-degree intervals, and we have obtained the 8 lunes of the domes. So the extrusion procedure has transformed the 2-dimensional rigid block into 3-dimensional rigid blocks, and also the 2-dimensional joint into 3-dimensional joints. These 3-dimensional joints are composed by devices formed of 4 axial links plus 8 shear links, 4 along the meridians and 4 along the parallels. Then we have not modeled directly the lantern at the top of the dome, but we have simulated its weight by applying vertical point forces at the top of the dome. Briefly, the results of the analysis are summarized in this slide. You can see the big corner rib and the middle of the lune, and the predicted crack pattern consists of main meridional cracks along the big corner ribs and minor meridional cracks at the middle of the lunes. And this is perfectly consistent with the actual crack pattern that you can observe on the dome in Florence. We have also computed the maximum compressive stress at the base of the dome. that at the base of the measured corner rib is 0.79 megapascal, at the base of the medium corner rib 0.78 megapascal, and at the middle of the loom 0.47 megapascal. Just to conclude, some pros and cons of this approach. The approach is a three-dimensional rigid block model with deformability concentrated at the joints, and its reliability, if we want, has been demonstrated by the analysis of the dome of Santa Maria del Fiore in Florence, and by the comparison of the predicted crack pattern to the existing one. Of course, the strength, if you want, so the pro of the procedure of the modeling is the extrusion procedure, because it allows obtaining many kind of structure, of three-dimensional structure. As an example, we can model domes complete with tool and lantern on a drum, church apsis, barrel vaults, cloister vaults, so all the structures that can be obtained by extrusion procedure. But of course, for an example, we cannot obtain a cross vault because it is not possible to obtain it by an extrusion procedure. This is a cons. This is a limitation of the actual procedure. Another pro, in my opinion, is the employment of distortions, which are Somigliano distortions, because this employment offers a significant alternative to the traditional methods of variable stiffness matrix or linear programming, as it addresses nonlinear analysis using tools inherent to structural analysis rather than purely mathematical ones. But cons, there is a cons that since an iterative method is necessary at the moment, the computational cost can be significant. So we are working to reduce the processing time and to use a single-step procedure. Okay, I've concluded. Thank you for your attention, and a special thank to my organizer of this special session, Antonino Iannuzzo, Natalia Pingaro, Andrea Montanino, and Ela Musavian. Thanks to all.
Okay, thank you, Stefano, for the presentation. I ask if there are questions from the audience. No questions? Okay, and so I would go to the last presentation by Vittorio Paris, entitled Structural Stability of Air-Guided Constructions. So please, Vittorio, if you want.
Hi, and thank you. Give me a second, I share my screen. Okay.
Okay. Okay, you can go when you want.
Okay. So you can see my screen and you can hear me. Okay. First, I would like to express my appreciation to the organizers of the special session, and especially to Antonino and Andrea Montanino. So today I'm going to present a research that is still ongoing on, that it's not completely, it's actually, I will present just a part of my research. As I said, the research is part of a bigger project, which title is Technology Application of Augmented Reality for Renovation Work. And as you can see here, we are working on combining historical construction technique and new technologies in order to provide better construction technique, better application for the building sector. The reason is, or the context is quite broad, but I think that it's mandatory understand and underline in this case why we are doing that. So since 10 years ago, 2016, McKinsey Institute report more or less this is just a a picture, a preview of the report, which title is Reinventing Construction, a Route to Higher Productivity. So in that report, McKinsey is underlying what are and how we can improve the efficiency of building sector. So 10 years later, we are still talking about the same factor that actually can improve the efficiency, the productivity of the sector. In the meanwhile, in the last years, at least after COVID until now, we are facing a big demographic decline that's is leading to a job vacancy bigger than ever, and with big issues about labor shortage. So with this context, of course, accounting sustainability, accounting environment-friendly construction, the impact of construction sector in the environmental in the world is one of the biggest in the world. But imagine a world that is eco-friendly without construction, it's not possible. So in order to make it possible, the sustainability of the construction sector, we should account not only the environment-friendly, but also productivity, efficiency, and the actual condition of worker. So here in this bigger project, we are working on design and engineering, on-site execution, technology, and capability building. These 4 factors are accounted in the research. And here now we can start to discuss about the contribution in this session. So imagine the project goal is building sub-horizontal structure without any temporary support in order, as I said, to increase efficiency, productivity, and sustainability. Here we have the technique, historical building technique that we considered tin-type bolting. Maybe you know, maybe not, I don't know. But what are the 3 key factors to build tin-type bolting is the first one, the tracing structure. The tracing structure are define the shape of the tile, and in the past, according to historical construction technique, are mandatory in order to provide the exact shape that is projected. The second one is related here to the construction sequences. If you want to build tin-type bolting, you need to follow a precise order of assembly. That means you have to place the first tile near the corner, and then the second, and then the third, as you can see here. The third one, of course, you need mason and you need scaffold in order to reach the position. In the project, we are working on the first and second factor. The first factor, the aim is to delete using how? Augmented reality. So in the project, we do not consider tracing structure, and we provide the construction sequence using augmented reality. But if we would like to avoid the use of tracing, and we want that people works and build today under this kind of condition, we need to be sure that the people can actually work in a safe area. And that means that we need to be sure that the structure is stable during its construction. Keep this in mind, we started to assume a case study, tiny vault, 1.4 meter per 1.4 meter, rise more or less 10 centimeter, as I said, sub-horizontal structure, made by bricks, which each one is less than 1.5 kg, and using fast setting mortar, gypsum mortar, gypsum base, and we consider traditional shape patterning. That means we consider the traditional pattern provided by the treatise and the historical knowledge, and provided by master mason that actually are quite few in Spain. So we combine, we put in comparison the traditional thin tile pattern to build this kind of structure we can see here with letter A, with another patterning we can see here with the letter B. And we design the assembly processes. The first picture, the first table here, the first square, is actually the complete structure. And then starting from the first line, second central column, you can see the construction sequences. So build an arch on the edge, then the second, the third, and the fourth, and then started to proceed assembly to lay the bricks in all the tiles in this manner. That means that at some points with the process A, you can see a spiraling pattern that because the structure will be built using spiraling, while in the process B, we actually build the structure laying an arch just on a side to another. So one arch side another one. So before build, we would like to assess the stability of the entire structure and the construction of the two patterns. We use discrete element method, and we consider standard material, thin tile elements, as I said, that's weight less than 1.5 kg, gypsum mortar, gypsum-based mortar, and what we obtain according to the discrete element analysis, run it or execute it under complete structures, more or less the same behavior. We can see the tiny effects of the blocks, but the maximum displacement is the same, and the distribution, the map, the heat map of the displacement is the same. But what happened during construction? So we use the same methodology, discrete element methods, and then we start to simulate the assembly of each construction sequences. That means laying brick by brick the structure. For model A and the traditional thin tile patterning, we see a displacement that actually is increased compared to the simulation run it on the complete structure. Here you can see at the first third, the third rings display a displacement of 2 sub-millimeter displacement, 0.2 millimeters. While at the complete structure, their analysis run it on the complete structure displays more or less the same behavior. So that means that if we simulate the construction sequences using discrete element model, we can actually evaluate the equilibrium during its construction. And starting from this, we executed the same analysis on the second model, the one that traditional mason, master mason, they do not want to use. They said that it's too dangerous. The collapse could occur. And actually, this happened. The numerical analysis shows the same behavior. That means that during construction, displacements occur at the lay of the third arch. You can see here, starting from the displacement under of sub-millimeter to centimeter displacement. Then we run the same analysis, increasing the hardening and the properties of mortar. And what we obtain is a stability, but with a bigger displacement than the previous cases. So here, then with this in mind, we started to build the structure in 3 different models using augmented reality and according to the patterning A. As I said, augmented reality will provide the tracing, the position of the bricks, and not only in general, the augmented reality check the right position, and only when the bricks or the tiles are laid in the right manner at the right time, the augmented reality will project the next sequences, as you can see here from the video, from the demo video. At the end, we ran it comparison between the digital model of A model, of course, A patterning, and the actual one. What we obtain is more or less this distribution of displacement or deviation, because we cannot say that is displacement or not. What we know that the volt shows in the blue area that are actually lowered compared to the digital model or the design model, and in the red areas where the bricks are higher or upper to the digital model. Interesting fact that the use of augmented reality denotes two peaks on the distribution deviancy between of the distance between the points that actually are surveyed from the real model and the digital one. And we can see here a valley that actually shows that augmented reality is affected, as the literature say, from drifting phenomena. That means that it depends from the position of the perspective of the user. What we are going to do now are test on mortar characterization, because we use value from literature, but it's not easy, and there is not wide literature in that consider the strength of the mortar after few seconds, few minutes to lay a brick. Then we would like to understand better what happened when you lay a brick, because the mason take a brick, lay in a position, and then settlement could happen. But using the standard survey methodology and tools is not readable. This phenomena is not readable. And if it's not readable, we cannot actually assess the right of the numerical analysis. And then we would like to run more tests in order to create a database statistically relevant with more or less shapes that actually can be used for further research. That's all. Thank you for your attention.
Okay, thank you, Vittorio. Is there any question? Okay, if there is no questions, I conclude the workshop, and thank you all again for your participation here, and see you on the next occasion.
Thank you. Bye-bye.
Thank you. Bye. Bye.